The mountain is the fragrances of nature have been as pleasant to us.
We trade with Exodus.
I know that none dare challenge me when I say I am an African. I am he who made it possible to trade in the world markets in diamonds.
Hello. Yeah, I was just going to confirm whether you can see and hear me.
Good morning, everyone. We seem to have lost our morning speaker. maybe she had too much fun last night. According to the program,
I'm here.
Is the chair of the session or our speaker here?
I am here. I'm just online. Can you hear me?
Okay, well, I can give you a talk. Let's.
I am online. I'm here. Can you hear me?
Are you here?
Yes, I am here.
Ah, there we go. There we go. The speaker is online. And is our chair online as well? Ah, there you are. Hi, Beatrice. I think I'm going to have to take over as your chair, Beatrice. I don't see the chair of the session. Is the chair of the session coming? Okay, the chair of the session will be in 5 minutes. Beatrice, sorry for the delay. Okay, so thank you very much, everyone, for coming. Before we get started, just very quickly, we made it. This is our last day. Thank you for coming to the morning plenary. Just a quick few announcements. So we'll have today we're opening up the exhibition area to our staff at the South African Astronomical Observatory and the South African Radio Astronomy Observatory. So you'll see some extra people around, but all people working for the astronomy community locally. Hopefully, we'll still have you here for the closing ceremony. Just a quick reminder that we've got one online talk, fireside. Oh, I think that might be a chair. We've got one online talk this afternoon at 2:30 with Kartik Sheth. And please, today is the last day, but if you are around during the lunch break, we'll have some informal entertainment in the exhibition area. So please join us there. The choir that has been providing entertainment so far are the ones that will be coming. So with that, give me 1 second. Let's see if this is our chair. Okay, our chair is on the way, but Beatrice, are you ready to start the talk? We can start in the meantime, and then our chair will arrive soon.
Sounds good.
Thank you very much. I'm sorry I can't introduce you as well as a chair would introduce you, Beatrice, but thank you very much for joining us online, and I'll hand over to you. Thank you.
Thank you. Right, I have shared my screen. I think that will come up in a second. But in the meantime, well, for those of you who don't know me, who I suppose is probably most of you, my name is Beatrice Bingo. I am currently a research fellow at the Open University in the UK. And from next month, I will be an Ernest Rutherford Fellow at the University of Hertfordshire, also in the UK. My work is mostly on radio AGN, and I am heavily biased towards radio data, and I have also worked with X-ray data. So just as a warning, I think my talk is probably going to come across as slightly biased towards those two wavelengths. But I have worked on AGN of different types. Today, I wanted to talk to you about multi-wavelength AGN classifications in the age of big data. Can somebody tell me if you can see my slides?
I can, yes.
Oh, good, excellent. So if you have your laptops or your phones with you, don't put them away, because I have created a little interactive activity for all of us to participate in the session. Just as a brief outline, I will be telling you a little bit about what an AGN is. Not everybody that is attending the session obviously is an expert on AGN. A tiny bit of history, then we will see whether we actually have too many AGN classifications or not. Try to understand why AGN are important, see what the various diagnostics at various different wavelengths are for AGN, how this applies to the age of big data, so the very large data sets that we deal with at the moment, and then just wrap up with some conclusions. If you were looking forward to this being a machine learning talk, I think you're going to be very disappointed. I suspect by trying to be inclusive in some ways, I would probably make people cross. That I haven't touched on the very detailed things that they want to learn about, but I hope that I will be able to still provide some useful information for everyone. So this is the interactive part of the session. There will be several slides that I will be sharing via Mentimeter. So it's a poll effectively. There will be some multiple choice questions and some word clouds for you to participate, and so we can all see the results and see where everybody is coming from, what everybody's perspective is on AGN classifications. So on your phone or on your browser, if you have a laptop with you, you can go to menti.com and then you enter this code 31895531, and you can start clicking to answer the first question, which is whether we have too many AGN classifications. And if I click on here, I can see that people are already voting. Can you see the little sliders coming up? Anyway, while that is going on in the background, and start talking, we'll revisit the question in a second when we have a few more votes. So it will be a bit of a nice surprise. So I guess we should start by defining what an active galactic nucleus is, or an AGN. And an AGN is effectively what happens when a supermassive black hole is actively accreting gas. As you know, most galaxies have a supermassive black hole in the center that has co-evolved with the galaxy throughout the history of the universe. And I could honestly end my talk here. Thank you for coming to my TED talk. This is probably the only AGN classification that we all agree about. There are obviously lots of details into what goes into this classification, but this pretty much is the in and out of it, and what everything else relates to. Even with this basic definition, there's some subtleties. So the Encyclopedia Britannica, if you read, everybody has a slightly different wording for this. Defines an AGN as a small region at the center of a galaxy that emits a prodigious amount of energy in the form of radio, optical, X-ray, or gamma radiation, or high-speed particle jets. These are all not mutually exclusive. You can have all of these at once. And the subtlety here is that this is not produced by stars. This is produced by something else. That's an important clarification that is not in this definition, but it's part of it. So something this doesn't define is what a prodigious amount of energy is. So I have put this picture of the shadow of the black hole in our Milky Way, this famous EHT, Event Horizon Telescope picture, because the black hole at the center of our Milky Way is not it's actively accreting gas, but at a very, very, very slow rate. So it's not actually considered an active galaxy. It's not considered an AGN, but there is some accretion going on there. So at the very low boundary, there's still some uncertainty in this definition. We know what happens when accretion is enough that we actually observe some of the effects through the electromagnetic spectrum. At the very low end, things are still a little uncertain. So even in this very basic definition, there is some disagreement. Before we move on, I'm going to go back to Mentimeter and see what people say. So I see that most of us agree that there are too many AGN classifications. Some enthusiastic people want more labels, and some people are not sure. All of these are valid opinions. None of these are wrong, by the way. It all depends on what you're looking for and what questions you are actually trying to answer. You can keep voting, by the way, until we get to the next one, but that will be in a second. So the structure of an AGN, where all the magic happens, you have a supermassive black hole in the center of the galaxy that is surrounded by concentric structures, effectively of gas, that is very hot close to the black hole, and it gets progressively colder as you get further away. And these structures, so that this is actually pulled out in 3D to try and understand it better, but this is like a donut around the black hole. And sometimes you also have a jet. So all of these structures have characteristic emission that we see throughout the electromagnetic spectrum. So close to the black hole, you can have, again, the base of the jet, and you can have some radiatively driven winds. You have a hot disk that emits in X-rays mostly. You have then a warm and turbulent disk that emits in the optical and UV and is responsible for the big blue bump. Then some infrared and optical emitting colder gas, and then what we understand as these two components eventually make up the torus, which we see peaking in the mid-infrared. And this is what AGN look like throughout the electromagnetic spectrum. So whether you have jets or not determines how much emission you see in the radio. And then this is the signature of the torus in the mid-infrared, the big blue bump, X-rays, and so on. And this is variable, so depending on the luminosity of the AGN, this goes up or down, and you get dominated by different factors. And this is obviously always superimposed to the actual spectrum of the stars and the gas in the galaxy. So you see more or less of it depending on the luminosity of your AGN. And these galaxies all look different depending on how much gas and how much star formation they have going on, and what other effects are going on in the galaxy. So it's complicated, and these things look very, very different depending on what part of the electromagnetic spectrum you're looking at. And this is why it took us quite a while to understand that AGN were all the same object. So as a very brief bit of history, the first observations of AGN were emission lines in NGC 1068 back in 1909 and jets in M87 in 1918. These were independent from each other. Nobody recognized that these were all the same class of object. Back in 1943, Seifert describes strong or high excitation emission lines in the spectra of some spiral galaxies, hence the class of AGN that we call Seifert galaxies. Then Victor Ampatsumian, a famous Armenian astronomer at the 1958 Solvay conference, explained that explosions in active galactic nuclei cause large amounts of mass to be expelled. For these explosions to occur, galactic nuclei must contain bodies of huge mass and unknown nature. This was one of the first it was one of the first times in which things, AGN were linked to explosions and mass being expelled and some form of feedback, and also one of the first instances in which they were associated with these bodies of huge mass and unknown nature, so what we now understand are black holes. It wasn't until the 3C radio survey in 1959 that we started associating radio galaxies with their optical hosts. And it wasn't until 1963 when we finally got the redshift of 3C to 7.3. So we were able to confirm that all of these things are obviously far away. They're not part of our own galaxy. We suspected it before, but this, for radio galaxies in particular, this was not confirmed until the 60s. So this is the reason why, these very different aspects that we see at different wavelengths, why the explosion of AGN classifications and AGN labels happened. So this is just a very quick summary of the most common classes of AGN that are still used nowadays. And there's about 50 labels on here. If we go back to Mentimeter, I wanted to ask you about what your favorite type of AGN or your favorite class of AGN is. And this is probably going to depend on what wavelengths you mostly use to analyze your data, what parts of the electromagnetic spectrum you're using to try and understand AGN. So you can type here. Yeah, you can see already words popping up. We'll come back to this in a second. And I suspect that many of these will overlap greatly with some of these classifications here. Some of them might not. This is not a comprehensive list. There are many classes of AGN that are not described here, and some of them we have just completely overridden because they are no longer relevant, or they have been superseded by classes that are more comprehensive. So yes, this does look like a lot. And obviously we need to make some effort to make sure that these classifications are relevant, that they are all physically motivated, and that they describe the properties of the sources clearly and in a way that is unique to that class. Some of these classifications are morphological, like radio classifications, such as the type 1 and type 2 von Arrow-Rayleigh radio galaxies, but they're all linked to physics. Some of them are based on absorption lines. Some of them are based on ratios of different types of different wavelengths that describe different physical mechanisms in place. For example, high and low excitation, or high and low, which are linked to high and low accretion rates, describe two different physical mechanisms of accretion in different types of galaxies, and their observational signatures. So again, another reason why AGN present in such a varied way throughout the electromagnetic spectrum is because some of the physics that underlie these processes are quite complex, especially if we start involving large-scale emission, as we do in the radio. Sorry, I did say I was going to be very heavily radio biased. You know, close to the central black hole, you're mostly involving things like general relativity, quantum mechanics if you're studying line emission, thermodynamics if you're studying shocks, you know, radiation-driven pressure, so on. If you start going into large-scale emission, you need to involve things like electromagnetism. I mean, you also need these to describe jets, special relativity, plasma physics, again, thermodynamics to try and understand how the interaction of these gas expelled from the vicinity of the black hole in the form of jets actually interacts with the interstellar medium and the intergalactic medium that's between galaxies. So fluid dynamics if you're trying to model these sources. So this is all quite complex. And this is why one of the great successes of astronomy, you know, regardless of your field, I think we can all agree that the AGN unification of Padavani in 1995 was one of the most successful ways to unify things that are very disparate throughout the electromagnetic spectrum, putting them together into a common physical mechanism, which describes these structures that I showed you earlier, where we have the central black hole and a series of concentric structures, some clouds of gas that get excited in different ways and that emit broad lines or narrow lines and can also cause some absorption throughout the electromagnetic spectrum. These are all in, you know, mostly signatures in the optical. These are X-ray to mid-infrared, and then we can have jets or no jets. Some of you might actually be familiar with this newer picture by Beckman and Schrader, who tried to separate the radio loud and the radio quiet AGN, so things with jets and things with no jets. And I have slightly amended this to show that you can have edge-brightened sources, edge-brightened radio sources at low powers. But in any case, this is still missing some of the physics. I'll get back to that in a second. Let me go back to Mentimeter very quickly and see what we have. Oh goodness, we have a very nice cloud of AGN classifications. I see people really like blazars in this session. Quasars, Seyferts, radio galaxies, lurgs, blazars, radio louds. So you can see, you know, if you look at this cloud, you can see how many people like the same kind of sources that you do, but also how many people like different things and might be seeing these complicated sources from a completely different perspective to the one you have. And I think this is something very important to bear in mind when you do research, what other people are doing and how they might be seeing your results and how they might be interpreting your results. So let me go back to the talk. The other key thing I wanted to talk about is why AGN are important. You know, it's all nice to try and understand these things just for the sake of understanding things. You know, we all want to do that just out of sheer curiosity. But AGN are actually really important to understand the evolution of galaxies and the evolution of the universe. And actually, I'll go briefly back to this. And I want to ask you which type of AGN feedback you think is most important. Even if you're not an AGN person, maybe you can guess. So radiative winds, these are things that are expelled from the vicinity of the black holes. This is purely driven by radiation pressure from this very luminous activity that is taking place close to the black hole, whether it's kinetic energy, kinetic feedback, which is linked to jets and shocks driven by jets, whether you think it's both or whether you're not sure. Again, all of these answers are valid, and I'll explain that in a second. And go back to this. So the two magic words I want to use in the context of AGN and the relation to the evolution of the universe are coevolution and feedback. This on the left is the famous Megavren relation that links the mass of a black hole and the mass of the central bulge of a galaxy. And you can see that it's actually a fairly tight correlation where both things obviously scale up together. And this is telling us that there is some common mechanism or a series of common mechanisms regulating the growth of both. So black holes and their galaxies have co-evolved, have grown together. And there's different ways in which this can happen. Obviously, things feed from the same gas. Galaxies grow from clumps of gas and mergers, and black holes feed from this same gas, but black holes also regulate the growth of galaxies so they don't grow too large. So there's common mechanisms driving both. The other important relation here is this one described by Silke and Mayman in 2012, when we have effectively the luminosity function, or the number of galaxies of a certain luminosity as a function of a galaxy luminosity. And if we did this from a purely theoretical perspective, if we only use the cold dark matter model to try and predict how many galaxies you would find at each luminosity, we would have this red curve here, but the observations actually show this blue curve here. So we have a lack of galaxies, a dearth of galaxies at low luminosities and at high luminosities. And there's two main mechanisms that we think are driving this. So at low luminosities, for small galaxies, is the supernovae winds and the explosions from supernovae that are driving away the gas and causing there to be fewer galaxies of this type. At the high luminosity end, we know it's AGN feedback that's causing these. It's these shocks from winds and from jets that are driving away gas, that are quenching star formation, and they're stopping galaxies from growing. They're heating up the intergalactic medium, stopping that gas from falling back onto the galaxy itself. Before we do this, maybe we should go, I don't know, let me continue with this for a bit and we can go back. So different accretion states, as I mentioned earlier, even the unified AGN model doesn't describe all types of AGN. If we go to how accretion works in X-ray binaries, which we are very lucky to be able to observe on timescales of hours to days to months to years, rather than hundreds to thousands to millions of years, as it happens with AGN, which are much, much bigger black holes and where processes occur on much, much longer timescales and on much larger physical scales. This is a plot that shows from Mureton 2004 that shows that the kind of accretion mechanisms that dominate a different accretion rate. So this is the Eddington rate. This shows things that have very little accretion scaling up to all the way as the maximum accretion that you can have. You can very briefly also go super Eddington, which is a completely different form of accretion where effectively you chuck more into the black hole than is reasonable, than you can maintain for long as an equilibrium. And this has slightly different effects. Most supermassive black holes in the nearby universe are actually in this kind of quiescent state where the black hole is accreting, but very, very, very slowly, and it's actually not really doing much. This is the case for our own Milky Way. If you go slightly higher in accretion rate, you have what in X-ray binaries is called this low heart state, where the disk is actually very puffy, it's optically thick, and you cannot see any emission from these structures. You cannot observe these as an AGN basically at any wavelengths other than in the radio, where you suddenly find these very powerful collimated jets that can reach very large scales in AGN, and you also see them in X-ray binaries. So this accretion mode, which is called radiatively inefficient or advection-dominated accretion, and it's described in these papers, is very, very effective at producing jets, both in AGN and in X-ray binaries, but it's very ineffective at producing luminosity. That's why it's called radiatively inefficient. If you go to this higher state, you get the disks that are described by Shakur and Sunyaev. This is where you produce lots of optical and X-ray luminosity, and where you can see these sources are AGN throughout the electromagnetic spectrum. You start finding all of these signatures. And in X-ray binaries, you don't expect jets in this state, but we do see them in AGN. So there are plenty of radio-large quasars and radio-large Seyferts out there, where we know that things are accreting at a reasonably fast rate, but we can still see the jets, which are turned off in X-ray binary. So this is not a complete equivalent, even though the physical mechanisms are similar. We know that there is something else in AGN that is actually able to drive jets in this state. And we think that magnetic fields are probably involved, perhaps the accretion rate of magnetic flux, something in the shape of the magnetic fields is helping AGN produce jets in this state. And here if you go Eddington or super Eddington, which is described by this physics here, you can produce jets very efficiently again, and you can produce lots of luminosity. So it's a slightly different regime with slightly different physics. And I know I'm probably going to make some people cross by saying this. In AGN, the radio-loud, radio-quiet division is not really a dichotomy, it's not really a binary, it's a bit of a spectrum. So I'll explain this in slightly more detail. There's extremes in the relation between how much jet you're producing and how much radiation you're producing. So for things like, Hydra A here, it's very clear that most of the output from the AGN is going into these large-scale jets, which are, creating these cavities that you see in X-ray gas in blue here, and creating these beautiful large-scale radio structures. That's where most of the energy is being deposited. in something like the Cecinus galaxy, which was a Seyfert and one of our nearest AGN, most of the energy from the AGN is being deposited, is being emitted in the form of radiation. This is a fairly bright AGN, and we can see all the effects going on near the nucleus. But this thing also has jets. They're just very low power jets. They are constrained within the host galaxy, but they are still doing some damage. They are heating up and shocking the gas within the host galaxy and changing the dynamics of that gas, the energetics of that gas, and potentially affecting the star formation of the host. So even in the regime where you are dominated by radiation, you can still have jets. You can have both processes. And there's all sorts of cases in the middle between these two things. AGN are variable. Accretion changes throughout the history of an AGN, even on relatively short timescales. So the radiation and jet mechanisms that affect the evolution of galaxies at low and high accretion rates have different effects, but there's a continuum between these two things, and sources can flicker between one and the other. They produce different physical effects, and they are different in terms of the physics that propel this emission. But you need to consider both. It's not enough to say something is radio quiet, therefore it's doing nothing, or something is radio loud and therefore I don't care about the other wavelengths. You need to consider these sources as a complete problem, as a multi-scale problem that links spatial scales, temperature scales, and physical scales. I actually liked this very recent review from Chris Harrison and Christina Ramos-Almeida, and I highly recommend that you read it. If we go back 70 meters slightly, I can see that the both seems to be the most common answer here. And yes, I would agree that it's both. It really depends on what physical scales you're looking at, what kind of structures you're looking at, and what physics you're trying to understand. If you only care about luminous AGN and you only care about the scales around the nucleus, then obviously you're going to be more interested in winds. If you care about large structures and the overall energetic influence of AGN, then maybe you care more about jets. But both of them obviously have some effects on the host galaxies, and both of them have some effect on the evolution of large-scale structure in the universe. Going back to the talk. Right, so how do we actually classify AGN? I've told you, the physics of these things are complicated. Things are different. AGN are different depending on what you're looking at, what scales you're looking at. So the first step is trying to match sources across multiple wavelengths. We're talking about multi-wavelength AGN classifications, and this is not straightforward. Back in the past, when we had very shallow surveys and the sources, the source density in the sky was very low, it was easy to just, put together different catalogs and say, this dot in one catalog corresponds to another one. Nowadays, this is not so easy. In Gaia, we have 1.8 billion sources, and even radio catalogs, which have some of the lower sky densities, now have tens of millions of sources. X-rays and gamma rays still have relatively low sky densities, but they have low positional uncertainties. And linking one wavelength to the other is not straightforward. Even if you only use, purely a distance ratio, this is an example from Pinot et al. 2017. Imagine that you're trying to combine sources from 5 different catalogs, 5 different wavelengths, and you have 5 dots that you have to relate to each other. So in the ideal case, you get something like this, where you know that all of these dots are associated. In the less than ideal case, these 5 sources are actually completely independent, and all the intermediate cases is how you actually try to link them. What is actually related to what? And you can use position, you can use clever things like likelihood ratios when you have some idea of what the sources look like across different wavelengths. I also recommend that you look, if this is something that you're interested in, at the N-way code and the N-way method led by Mara Salvato and her team. As I said, this is not a straightforward problem. And it becomes even more complicated when you start cross-matching things that are extended and things that are point-like. So these are all data, these are all images from the LOFAR Galaxy Zoo for the second data release of the LOFAR to Meter Sky survey, which is a radio survey carried out at 150 megahertz. It has about 4.3 million sources, and it covers about 27% of the northern sky. And these are some of the complicated cases that we couldn't deal with automatically. We do have likelihood ratios, and we have ways to optimize these likelihood ratios based on the extended morphology of a radio source. But radio sources live in groups and clusters, and sometimes you have really messy cases and you actually need people to look at them. We don't know for much longer that is going to be the case. Obviously, when you start classifying millions of sources, even if you just go and ask regular humans who are not astronomers to help you look at these things, you might not get many people volunteering. You might not get enough pairs of eyes looking at these things. Sometimes you actually do need experts for this. But yes, you can see these are all messes. So the yellow contours actually show the radio emission, and this is superimposed on some optical or on some optical maps, but you can see the actual galaxies that this emission is coming from. Ignore the ellipses in this case, and you can see, yes, so trying to link this emission to what galaxy or what galaxies it's actually coming from is very straightforward. Which one would you pick here? Even if you use symmetry criteria, there might be more than one that is contributing to this emission. Sometimes you have things like this, where there's a superposition of galaxies that might actually be merging, and you can see that some of the emission is linked to this one, but there's some that is linked to this one as well. This source, if you only look at the radio contours, you might think, this is a classical double radio galaxy, and there's probably a host in the middle. Because LOFAR is so sensitive, we're actually seeing star formation processes happening as well. So in this case, it's actually a merging pair of galaxies, or you have something like this, where again, there's a blob of emission that probably comes from here. There's some more emission that probably comes from there. There's some of the stuff down here. Where is this coming from? You have to put all of these together into a catalog, and it's quite complicated. So before we move on to the electromagnetic signatures of AGN at different wavelengths, I wanted to take you to the next part of the poem, which is going to ask what your favorite telescope or survey is. This is another word cloud, so you can start typing in. You only get one choice, so pick wisely. And this is probably going to tell me how much you're going to like what I'm going to say in the next slides, and how cross you're going to be with me for not citing your favorite papers. So this is not just because radio is my favorite. I'm doing this in from low to high frequencies, or from longer to shorter wavelengths. In radio, classifications are partly based on morphology and partly based on spectral shape. So the most famous classification for radio galaxies is, for radio sources, is probably the one by Fanaroff and Riley in 1974, which is morphological and is based on whether a source is bright in the center or bright in the edges, and this links to where the jet is getting disrupted. So where the jet is interacting with the surrounding medium and depositing most of its energy. So even though this is just based on putting things in buckets depending on what things look like, there's some underlying physics there that are causing these sources to look the way they do. Then obviously we do have things that are pointing towards us. Not everything is in the plane of the sky. So these are blazars or BLACs. We have sources that like quasars, where some of the emission might not be extended. We have compact deep spectrum and gigahertz peak spectrum sources, which have different spectral properties, but they're also compact. Some of these sources are just young and they haven't grown into these very large scale emission. Some of them are just compact, they are short-lived, they never really grow past this stage. In some cases, we cannot really tell, we just don't have the resolution. We are now starting to have the resolution to be able to see these structures, even at higher redshifts, not just from LOFAR, which I mentioned here, but also for other surveys. We also have all sorts of bendy sources. As I said, these sources live in groups and clusters, and they interact with their environment. They travel through these clusters. There's all sorts of funky things going on with the cluster environments where these things live in. So wide-angle tails and narrow-angle tails are two different ways of classifying these bent sources, depending on the opening angle of the jets of these structures here. But a lot of these classifications depend on what your resolution is, what your sensitivity is, and what frequency you're looking at. Things look very different at low radio frequencies as they do at high radio frequencies. And this is something that we need to really keep in mind when we are classifying radio galaxies. I really recommend reading this paper by Larry Ratnick from 2021. And something that we also must bear in mind is that, most of us really like these extended things where we can actually do lots of fun physics and try to understand all these funky things going on. But even for the deeper surveys that we have nowadays, most radio sources are compact, or they are point-like, at least in the surveys that we have. So when we associate things, the majority of the population is going to be point-like, just like the extended ones. And radio can get really, really complicated indeed. This is just a really fun example. This is from a paper by Marisa Brienza et al. Back in 2021. And this is trying to trace back the activity of a black hole who's created a massive mess obviously in an environment. And from this little radio galaxy, you get different epochs of activity, and then you get all of these messy things happening in a cluster that produces this shape that I like to call Tom Bombadil, after one of Tolkien's Lord of the Rings and Hobbit characters. It looks like an old person with a hat and a very long nose or a pipe. So yes, radio can get pretty complicated and pretty fun when you actually try to understand the dynamics of what's going on. I've put some papers up for you to read if you're interested in radio sources. These are just some recent reviews. You don't have to write these down. I'll put the slides and you can do this later. In terms of infrared emission, you go obviously from far infrared to near infrared. It's a very, very wide wavelength range. The typical uses of these range are, you get things like emission lines that allow you to classify different types of AGN and to understand when something is dominated by an AGN versus dominated by a galaxy. You get different emission profiles at different wavelengths throughout the infrared spectrum, and the physical mechanisms producing this line emission are telling you something about the physics underlying this emission, and something about the what is heating the gas, what is how long-lived this emission is, and how broad this emission is telling you something about the velocity structure of that gas. A lot depends as well on how luminous your AGN is compared to the galaxy. So in this plot by Patrick et al. 2015, you can see for different AGN luminosities how much of the profile of the galaxy you can see. And obviously, as the AGN gets more luminous, it starts completely swamping the emission from the galaxy, so you cannot really tell what's going on in the host. You can only see the emission from the AGN. Infrared is very useful to trying to constrain the effect of the torus, so this very large structure called the structure that is around the AGN. It might be one of the best wavelengths to try and estimate the bolometric luminosity, so the overall luminosity of an AGN. And it's also very good when you're using sublimeter or far infrared to see regions of ionization versus shrouding, and to try and understand how you can separate star formation and AGN activity. In the optical, again, the dominating processes that we study are emission lines, and these are used to produce some of your favorite AGN classifications. So whether you're dominated by the continuum from the AGN, as in this BL-LAC, this is something that has a jet pointing right towards us, and this is completely swamping any other emission you can see from the galaxy. You have a quasar where you're still dominated by the AGN continuum, but you can see some of the stuff. CFIT galaxies of different types, and low excitation galaxies or liners, where some of these high excitation lines that you associate with AGN emission are not happening, but there might still be an AGN there, versus galaxies that really don't seem to have any nuclear activity at all, broadline radio galaxies, and so on and so forth. So obviously you link this to what is going on at all the wavelengths. But optical is perhaps the most popular wavelength in how AGN have been classified, and this is probably what has caused some of the label explosion that I described earlier. And optical and UV are not just useful in emission, they're also useful in absorption. This is telling us some of the properties of the colder gas that is in the way between us and the black hole within that host galaxy. So these are just some examples to show you some absorption profiles. You can also do this with infrared. You can see silicate absorption that is linked to these denser clouds of gas. In the optical and the infrared, we also have very high resolution data, be that from ground telescopes using integral field spectroscopy or IFU, where we can put many optical fibers onto a relatively nearby source, and we can get detailed spectra for different spaxels, different pixels in this source. So we can get velocity structures and gas properties and spectra throughout across an entire galaxy. Then with things like the James Webb Space Telescope, which I'm showing you some images of here, we have very, very high resolution, in this case, infrared maps of nearby galaxies or relatively nearby galaxies, but also far away galaxies, where we can really zoom in and try to separate spatially. This is for different emission lines, what the surface brightness looks like across a galaxy, across an object, what the velocity structure of the gas is, and the full width half maximum, so how wide these emission lines are across different places. And this is really helpful when you're trying to separate AGN emission from star formation, from the gas that is surrounding it, but also when you're trying to understand the dynamics of the gas around an AGN and how this AGN is being fueled, or what type of effect this is having on its surroundings. In the UV and soft X-rays, things are still, dominated by some emission lines, particularly in the UV and again the soft X-rays. The gas is so hot that it's producing these emission lines that your heavier elements are starting to look like hydrogen and helium. So you have oxygen that has the transition that you usually expect in hydrogen and helium. Again, I don't expect you to understand all of this. It's just funky lines that you can use to diagnose how bright your AGN is, what processes are dominating the emission in this AGN, and what effects it's having on the gas of its surroundings. And variations in these lines are telling you about accretion state changes, for example, or accretion rate changes, and what is going on in the areas that are closest to the black hole. So things like reverberation mapping, trying to map changes in luminosity and changes in the profile of some emission lines, although that is usually done at harder X-rays, tell you something about changes in the accretion disk very close to the black hole. I've put some recommended reading here. There's many other papers. I'm just trying to recommend some that I find interesting. X-rays are also perhaps one of the best bands to try and constrain intrinsic absorption. I hope you can see this as a video. This is what happens to an X-ray spectrum. You have the famous iron K alpha line. This is the energy in kilo electron volts. As you start increasing the absorption column, so the neutron hydrogen column within the host galaxy, or perhaps even some foreground absorption from our own galaxy, you stop seeing some of these emission in the softer bands. The iron K alpha line usually survives for a while, but as you start getting into the Compton thick regime, you mostly miss all the emission that you can map up to 10 keV, which is the kind of wavelength that you see with like XMM or Chandra. And you have to go to the very hard X-rays to actually see the component that is linked to the AGN. In X-rays, you can also use extended emission to try and understand the dynamics of some of the shocks that are driven by jets and the large-scale emission. These are just some quick examples where you can see these maps show X-ray emission and some radio contours, and this really allows you to constrain the energetics of these large-scale emission linked to jets or large-scale outflows. And you can also this is a very famous image of the Perseus cluster, where you can see some of the echoes of different emission episodes, or different outflow episodes from the galaxy at the center of this cluster, and how it has created echoes. How this is like fluid dynamic. How these echoes have propagated through the fluid gas of this cluster. So X-rays are also useful to understand some of the large scale emission. For gamma rays, you have gamma rays of two types, say linked to non-blazar AGN, so radio galaxies, and linked to blazars. This is mostly the kind of diagnostics that you do at gamma rays when it comes to AGN. You also have some X-ray binaries there. But as you can see, the density of sources is quite low. Gamma rays, this is from Fermi. They have also low positional uncertainty. This is going to get better with things like CTA. So linking the gamma ray emission to what galaxies has actually caused that emission is far from straightforward. So this is an overview. Let's go back to Mentimeter to change these. So I can see that, okay, we are heavily radio biased in terms of favorite telescope here. There's plenty of people who also like JWST, as there's some for Gaia as well. Oh, this is very nice to see. Again, this is something for you to reflect on. This is how many people actually like the same telescopes that you do, but how many people also have a very, very different view on AGN based on the kind of instruments that they might use. So understanding their perspective is also important. It's very nice to see some love for integral as well. So for the next question, and I'm going to change back to the presentation in a second, I wanted to ask you which of these two galaxies you think is an AGN. So these are two spectra from SDSS. This is Galaxy 1 and this is Galaxy 2. And I'm not going to say if you paid attention to what I just said, this is probably better for anybody who has seen optical spectra before. I want you to try and guess which of these two galaxies is an AGN. I'm going to move slides, but you have little snippets of these two spectra in the Mentimeter poll. And I'm curious to see what you'll come up with, what the opinion and what the agreement is going to be on this one. So in an ideal world, we would have all of this multi-wavelength information that I have just described, with impressive sensitivity, great resolution, and we'll have millions of billions of sources that we can just classify, all at our fingertips. We would also have, beautiful SED models, beautiful diagnostics, and beautiful methods that we can use to feed all of this data in a very computationally efficient way, and we would gain perfect insight on all AGN populations and all of their underlying physics, and then we would all be happy and we would soon be out of a job. But unfortunately, this is not the real world. The real world is a lot more limited, it's a lot more complicated. We often have very patchy, limited, or even wrong information where, two catalogs that have been combined together have not actually associated the right sources, for example, or where we have some instrumental effects that are hindering the observations. We also use models that do not account for every kind of galaxy or every kind of AGN. There are biased towards, for example, galaxies that don't have AGN and they're better at constraining star formation, or are biased towards X-ray luminous or optically luminous AGN, and they don't calculate star formation just as well. We use things that are imperfect, not just imperfect data. And we also have to rely on diagnostics that are limited, again, because our information is patchy, is missing. We have to do analysis that maybe is based on just one wavelength or just one line ratio or just one observational little bit, and trying to constrain the overall properties of a whole subpopulation of AGN based on these limited diagnostics or techniques. There are a few things here that I want you to remember. One of them is that AGN are variable and they're transient. And this definition from this recent review by Chris Harrison and Cristina Ramos Almeida, I really like. AGN are not objects, they are events. So a galaxy sometimes has an AGN, and sometimes the AGN has jets, sometimes it doesn't have jets, sometimes it's a quasar, sometimes it's a Seyfert, sometimes it's something, and sometimes it's just sitting there, it's just a passive black hole that's doing nothing. So these things change, and sometimes they change on very slow timescales, sometimes they change on very fast timescales, but this is something to remember. AGN and galaxies co-evolve with redshift. So if you come up with a diagnostic, or if we come up with a diagnostic that's based on low redshift populations, these might be very wrong when we try to extrapolate it to the high redshift counterparts, which is inevitable when we get new data at much higher redshift and we try to understand it. First, we're going to link it on, to what we know, but we need to then analyze that separately to try and fix any biases that we're imposing, that we're dragging from understanding a population of sources that is very, very different. And I wanted to try and think that classifications are not set in stone. This is particularly important for radio galaxies, which is why Larry Ratnick proposed that we use tags and not labels. But again, objects, AGN change. You might have different data at different times that allow you to see more or less insight on an AGN. Even when you get better data that allow you to establish the properties of a source a bit better, it's still important that you keep the information on what it was classified as before, because there might be other sources where that information is not available, and where you can actually link what you see to the physical mechanism that's underlying what you're seeing, what you're not seeing, if I'm making sense. So depending on what you're using, you might classify an AGN as a certain type. Depending on what somebody else is using, they might give that thing a completely different classification. That is all based on limited information. It doesn't necessarily mean that one of you is wrong. It's important to document all of these, because that will relate to what all the sources are going to look like with different instruments. So back to Dimitri for a second. I want to see what your responses were. I can see some bias here. I mean, I don't think there are really wrong answers here. I want to say perhaps number 2 is the wronger of all of them, but I haven't really been fair to you. This was definitely a tricky question. Nobody told you there was going to be a test. I haven't really told you what I defined as an AGN here. What type of AGN was I referring to? What parameters was I going to use? I did show you 2 SDSS spectra, but I didn't really show you all the information on these 2 sources and what they look like at different wavelengths. So none of you thought neither. So I guess some of you might have thought, okay, these are probably 2 AGN and you're just tricking me. Somebody might have thought, oh no, you're actually showing me a boring galaxy in an X-ray binary. But nobody thought I was tricking you in that way. And not sure is probably the most correct answer, because you need more information to actually be able to tell these apart. So if I move on to this. So this is, again, SDSS cutouts of these 2 galaxies. The first one is NGC 5548, which is it's a famous Seyfert galaxy in a spiral host. It's quite well known. So yes, this is definitely an AGN, and you did identify that it has AGN signatures in the optical. The other one is NGC 6109, which is a famous 3CRR radio galaxy. And if you look in the optical, you have a just typical elliptical galaxy, massive elliptical galaxy spectrum, no signatures of an optical AGN. But if you look in the radio, oh look, there's a very powerful radio jet here. So this is definitely an AGN as well. It's just not showing up as such in the optical. So both are actually AGN, but I wasn't fair to you, and I didn't give you all the information to actually be able to tell these things apart. So this is just to show you some of the risks of working with limited information, and just to make you reflect on what might you be missing when you try to do classifications and you don't have all the information available. Again, depending on the question you're asking, if you're only interested in optical AGN, then just classify this one as an AGN is fair. Just be mindful of what you might not be talking about, what you might be missing out on. Let me see what the next Mentimeter was. Right, so before we get onto this is a question I plan to ask later on, but you can start replying on right now. Whether you're planning to use machine learning or AI for your research in the near future. In the near future here refers to the next few years, not just the next few months. So say 2 to 5 years in the future. In the meantime, I'll tell you about what happens in terms of AGN diagnostics when you have limited information. This is not comprehensive. I'm just going to show you some examples of how we try to pull these things apart, how we try to classify these things, how we try to understand what's going on based on different techniques and different wavelengths. So BPT diagrams, many of you are probably famous, many of you are probably familiar with, they're very famous. It's a way of trying to separate star forming, composite and different types of AGNs. So liners, again, this is low luminosity AGN. You can get liner emission from star formation, but it's quite rare. To try and separate all of these different types of galaxies, some AGN dominated, some star formation dominated, some in the middle. This is just from a review by De Souza, who actually proposed a probabilistic Gaussian mixture model to try and understand this from a statistical standpoint. So this is already entering into the big data regime, trying to do this for large populations of sources. This is a technique led by Stephanie Junot. It's called mass extinction, and again, it's based on the O3 line and H beta line versus the stellar mass of the galaxy to try and separate star-forming galaxies from AGN, and you can see that there is some contamination. Both of these techniques work really well, but they're not perfect. None of the techniques are perfect. None of our data are perfect, and that's something always worth bearing in mind. And I'm only mentioning two. There's many other things that you can use in the optical. In the mid-infrared, perhaps you're most familiar with these types of diagrams. So this is based on Spitzer data. This is based on WISE data. This is from one of my papers. It's not because I want you to cite my papers. This is just to show you that I also use these diagnostics. I'm not just, preaching to you not to use them and how bad they are or how good they are, but I also use them in my science to try and understand what's going on. These are all AGN. These are all radio galaxies of different types. And you can see, this is the famous Stern wedge to try and select radiatively efficient, so optically luminous AGN in the mid-infrared. And this is the WISE color plot. You would select sources here with different types of wedges, like the Mateos et al. 2012 wedge only selects things up here, for example. And again, is to try and select AGN that are dominated by emission in the optical mid-infrared and so on. So not just AGN that look like AGN in the radio. And you can see that even if you only want to select this high accretion rate, optically luminous, X-ray luminous AGN, you still get some contamination. However restrictive you make the wedge and however optimal you make the wedge based on these color plots, you're still missing out some. And obviously both here and here. And obviously you are also missing out all of these other AGN, which are dominated by the hosts in the mid-infrared, where you just see them as AGN because they have powerful jets. And again, there's a long list of things here that you might want to read if you're curious about these diagnostics. I'll put the slides on so you don't have to write all of these references down. In the radio, we have extra problems in terms of, sources look very different depending on what radio frequency you're looking at. It's not the same to look at, 150 megahertz as it's to look at 1.4 gigahertz or 5 gigahertz. You're actually mapping very, very different structures and very different electron populations. So this is an example from Mahatma et al. 2019. where we have contours from LOFAR in yellow, and we have VLA emission in black. And you can see that 1.4 gigahertz VLA emission only sees this newer episode of activity for this radio source. But when you actually look at lower frequencies, which can map older electron populations, so older episodes of activity, you can actually see the remnants of emission from a previous epoch of activity of this thing. So it switched off the jet for a while, and then it started it on again. This is from an IMPREP paper by Bonnie Barkas, led by Bonnie Barkas, where you have a LOFAR source down here that then you observe at higher frequencies at 1.4 gigahertz with the VLA, and you might classify the thing as edge brightened. Once you get to the higher frequency, you see that these are not really compact hotspots, but they're more like diffuse lobes that are probably aging. And oh no, you see a core that you couldn't really see in the low frequency data, and this is suddenly more center brightened than edge brightened, and you would classify this thing differently, and it's probably also restarting. In this example that I showed you earlier from Gendron Marcellet 2020, where if you only saw this bit of the source at high resolution, you might classify this as a wide angle tail. If you actually see these two tails being dragged at a very relatively small opening angle, you might classify this thing differently. So depending on what information you have, you might classify sources in a very different way, and you might infer different physics and different effects based on this. This is an example of stacking, spectrum stacking, which has been very popular in X-rays. This is an example from the X-rays trying to do spectrum stacking of faint sources. LL, LM, HM, and HH all refer to redshift and luminosity. So this is low luminosity, low redshift. This is high luminosity, high redshift. To try and get more information out of the spectrum than you would if you had an individual galaxy, which is dominated by noise, which is at the kind of the limit of what your instrument can detect. And X-rays, as I said, this is a technique that's been very popular because in X-rays, you actually count individual photons. I've had a spectrum where I name my photons ini, mini, mini, and mo, because I only had that many of them. But it's also extended to other wavelengths. I hope that Marina Nodova will forgive me for doing slight spoilers on her work that stacks SDSS spectra to try and improve the signal-to-noise ratio of emission lines for different source populations. The key with stacking is that you have to do very clear preselections and very clear grouping of your data to make sure that you're not introducing even more noise, that you're really stacking things that are supposed to look like each other to actually recover this kind of signal. And in terms of broadband modeling and broadband SED fitting, this is results from Best et al. In 2023, where they used SED fitting codes, different SED fitting codes to try and understand the different properties of a very large sample of lots radio AGN. So using MACVs, backpacks, two types of methods for SIGAL and AGN fitter. This is to try and derive the star formation rates for the same kind of sources, star forming galaxies in AGN, and also some bad fits. And you can see that all of these SED fitting methods produce slightly different results. So you have to understand where these results are coming from, and depending on the parameters that you're trying to derive, you might use one or you might use the other. So if you want to constrain, for example, AGN luminosities, AGN fitter is going to do a better job. If you want to constrain the star formation properties of a sample, something like SIGAL or MACVs or backpipes might do better. And in some cases, you have to reach a compromise to try and find which of these values is best. But sometimes you actually need an average of some methods. So you really need to be careful with how you use this data. And this is some examples of applications of these results. So if we go back to Mentimeter again, I see that a lot of you are very enthusiastic about using machine learning or AI in the near future. Some people are still reluctant, and some people are not sure and just want to find out more before making that decision. All of these are valid answers. All of these are good answers. It really depends on the data you have, what you actually want to do with them. I suspect that this fraction is going to increase in the next few years. It's already much higher than it probably would have been even just a year or two ago. So, oops, accidentally skip there. Let me also move this on. So this is for you to do at the end of the survey, and just leave it on so we can start accruing votes. Whether you still think we have too many AGN classifications, I'm curious to see how that opinion has changed. But going back to the presentation, sorry. The age of big data. By big data here, I mean that we have too many sources. We have too many details in our data to just classify things by hand and classify things by eye. We no longer have the luxury of just sitting down with a print and trying to draw contours by hand on a piece of paper, or to use photographic plates and look at individual sources by eye or by hand and trying to really look at sources individually. For good and for ill, we can classify populations, we can understand populations broadly, and we can get better understandings of their underlying physics by doing it this way. When you're looking at just one or two or a handful of sources, you don't know whether those are the norm or the exception, and how representative they are of the entire population that you're trying to understand. But single source studies are still important. If you want to understand the detailed physics undergoing some of these processes, single source studies, multi-wavelength studies of an individual source or a few sources are still important. They still have a place. But even there, the volumes of data that you have to reduce and to process are huge. So you need some sort of automated method. Modern astronomy also demands a faster turnaround. Some of these is, the fact that your data are going to become public, they're going to become open source, and somebody else might use them, so they might scoop you. We want faster publication. We demand more publications and more high-impact publications for career progression. Things are becoming more competitive. Again, the trade-offs there is good and bad. We have a plethora of data that we can easily access, even if we're not part of that collaboration, we know we can wait a year or two and get them. But at the same time, we have to do something with our data pretty quickly. And we also need approaches that are more computationally efficient. We don't have the luxury of just waiting months for something to process or for some data to reduce. Even citizen science is not fast enough sometimes, or it's not good enough sometimes. And this applies to both data processing and analysis. We can't sit for ages with IRF or something anymore to try and reduce data, to try and calibrate data. We need to do things efficiently and quickly. This is also more efficient for the planet. With the volume of data we're processing and the type of computational processes we're using, we need to try and minimize our carbon footprint. And yes, there are always risks. We need to be careful with the analysis. We might miss interesting sources. On a first approach, maybe we're just trying to model the bulk of the population, but then later on we can go back to the data and model the outliers, which might give us some really interesting insight on what's going on. So we need to have good archive policies, good archive access, and make sure that we still use the old data. The fact that they're old doesn't mean that they're not useful, or that they're not good anymore, and that they're not going to show you something new. So we need to maintain those data so we can revisit them in the future. It's also a case that, when we try to model the bulk of a population, or we try to extrapolate, we might be introducing some systemic biases. So revisiting data is always a good idea to try and minimize that effect. This plot here is just showing you the number of sources that you get, in this case, again, from radio catalogs. Optical catalogs are always 1 to 2 to 3 orders of magnitude bigger than this. But you can see that even in the radio, we have tens of millions of sources now, and we're obviously going to get another order of magnitude or so on this when we get to the SKA. As I said, Gaia has 1.8 billion sources. So, these are not numbers that we can just classify by eye. So how to approach the problem of, big data? How do you do this modeling? How do you do this if you haven't done this before? The first thing, and I think this is something sometimes we forget as scientists, is we need to understand what questions we're trying to address. You need to start everything with a science question and something that you actually want to test. It's nice to just see, what happens if I throw this model at my data? What do I pull out? To try and understand what you're pulling out, you need to understand the physics, and you need to understand the questions that you're trying to answer. The second thing is you need to understand what the biases are in the data you're using. There's always going to be biases. No data are perfect, no methods are perfect. What are you missing, or what is overrepresented in your sample? What are you trying to pull out from these data sets? What part of the population is going to describe? And then you need to try and figure out what method is most appropriate for your data and your objectives. So maybe citizen science is enough. Maybe you have a very complex problem and the numbers of sources are not so high that you cannot ask other people to help. Maybe this is something that humans still do better than machines. Maybe what you need is a statistical method, something that just puts things in boxes based on some parameter. Maybe you need some sort of algorithm or some sort of code that just pulls things out of a series of images or a series of spectra. Maybe just some image processing and image analysis is what you want to do. Maybe you need some simulations. Or you can go the machine learning route and you can do either supervised or unsupervised learning. And in a nutshell, effectively, supervised learning extrapolates from known patterns or samples, and it's really good for classifications. Initially, we have used a lot of supervised learning in astronomy because it's great for classifications. But it does need large samples of labeled data, which are obviously all intrinsically biased. So just because this is being done by a machine, it doesn't mean that it's not biased. Any machine learning method is only going to be as good as the data you put into it and the parameters you put into it. It's also computationally expensive, and it's less effective for complex problems. So if you are trying to answer a simple answer, if you're trying to find a simple answer, and you have a large sample, maybe supervised learning is for you. For unsupervised learning, you effectively cluster data in different ways with different algorithms based on intrinsic characteristics of those data. These intrinsic characteristics, and these data are still being fed by humans. So again, just because the machine is producing an answer doesn't mean that the answer is actually perfect. You don't have any pre-existing labels and categories. So this is great for serendipitous discoveries or trying to understand new patterns and discover new patterns and grouping data in different ways. But these algorithms can be very non-transparent and they can be very difficult to interpret. So if you use unsupervised learning, make sure you test things, make sure you inspect things, and that you describe the outcome and the method properly for people who might not be familiar with this, because otherwise the results are not going to be useful. And you also have an intermediate thing. Semi-supervised learning is a thing, maybe not used so much in astronomy, but it's definitely used in other fields. I'm not going to read through all of these. This is a very good summary I found on this website of the characteristics of supervised versus unsupervised learning. So, in terms of input data, what you need, what the computational complexities, there's even a quick summary of the different algorithms used. So at a glance, how one compares to the other, how you can test or not test the model, and how you can do different types of classifications, what things are useful for, how much supervision and how much babysitting you have to do for this. There's two relatively recent reviews here, one from Barron 2019 about just using different applications of machine learning in astronomy. This one by Fotopoulou 2024 focuses only on unsupervised learning in astronomy, which, as I said, has been the minority. And even this review has like 250 references. So this is a booming field. This is something that has just exploded in the past few years. And we're still trying to figure out what methods work best for which data set. Some examples of what we can do with large volumes of data. I'm trying to summarize a few here. This is not comprehensive. I'm probably going to miss all your favorite papers. I'm sorry, but these are just things I think are interesting that you might want to know about. So in the context of LOFAR, again, showing my bias, this is what I use for my science. Bonnie Barkus led a technique called the reach line, which traces the path of the jet throughout a given radio source, tries to find the path of maximum emission with some erosion and some algorithms to try and trace this path. And this is really useful for characterizing extended sources. It's also really useful combined with maximum likelihood algorithms to try and figure out where your host is, to try and predict where your host is. So you know something about the host already in terms of what it's going to look like. The host of a radio source tends to have a particular SED profile, a particular set of characteristics, but knowing where it might be along this reach line actually really constrains the type of, the number of objects that you can try and put into this maximum likelihood algorithm. And this is why this has been incorporated into the LOTS-DR2 pipeline. Lucy Cluse, who is a PhD student, is actually leading some work on using unsupervised learning and reach lines to try and map the bendiness of sources and to try and map these onto different AGN classifications. So you can adapt this to machine learning techniques as well. This is some work led by Raphael Mostert in using unsupervised learning to cluster different types of LOFAR sources based on their morphology and seeing how the machine does this and how this maps onto the classifications that we have given in the past by eye. These are some examples from SDSS. This is unsupervised clustering of spectral data from SDSS to try and you can see that there are some very high numbers and some lower numbers here based on different spectra, how you can cluster different types of sources. And this is an example of unsupervised learning where you have an algorithm that detects different sources on a photometric image, and then it combines photometric data across different filters to try and recover classifications of different types of sources, so quasar stars and galaxies, and it has a certain precision and a certain recall. And obviously these are all improvable. This is work that is still being progressed on. This is an example from the gamma rays, which I thought was really impressive because the number of sources that you get in gamma rays is actually pretty low. So this is an effort to use supervised random forest to identify AGN impulses in the 4th Fermi Large Area Catalogue, and it seems to have really high reliability for something that has, again, a relatively low number of sources. This is an effort to try and get better constraints on redshift. It's based on it's fed from about 15,000 X-ray detected sources, fed into an algorithm that's called CircleZit. And it's a fully connected neural network. So this is supervised learning again. And the aim is to use all of the redshift-dependent information in the spectral energy distribution to try and gain insight into redshifts. And this is an example of, this is how the scatter is working at the moment. There's this, again, some improvements still being done on this. Most redshift estimations, and even with SEDs, use optical lines to get the redshift. So this is an effort to try and classify that in better ways. There's also applications in lensing. For example, Agnello et al. have led a number of papers on lens quasars using machine learning. Just lensing in general, not just applied to AGN. There's an interesting paper led by Josh Wild in 2022. So all sorts of examples of how you can apply different techniques to different data sets to pull out interesting information and then use that to do science. So before we got to the conclusions, let me go back to Mentimeter as well. And I see that, the results have changed a little bit, but they haven't really changed that much compared to the first slide. If I go back, I think there's actually more people who say that we have too many AGN classifications. Yeah, that's at least a number of not sure. All of you have been more decisive now in saying how many AGN classifications we have and what you think is right or wrong. So yeah, this is interesting, just so you can see everybody's perspective on this. Going back to the conclusions, AGN classification is really complex. We are using limited, very biased information to classify sources which are really variable, which evolve, which present very differently at different wavelengths. It's a really complex problem. And classifications, I'm not saying don't go and classify things, that would be very hypocritical of me. My most successful paper to date is all about putting things in boxes and actually inventing a new label. So I'm not telling you don't classify things. Just when you classify things, try to do that in a way that is physically motivated, that is actually describing the physics and is describing intrinsic properties of the population in relation to everything else. And consider using tags, not labels. So classifications are not absolute. Always, regardless of what you do, please check your bias. Choose your methods carefully and understand what is missing from your data, what is overrepresented in your data. I'm very badly paraphrasing Spider-Man here by saying, with powerful methods comes great responsibility. Consider that your results might be used as an input to design a future survey, to design a future model, and that any biases that you have will be baked into that in the future. It might actually set a lot of people back if your results are not correct. And arguing again for, working towards good archive policies and using data that are already there, not just the data that are just the newest and most fashionable. So I'll leave things here. Thank you very much for your time.
Okay, thank you very much, Dr. Beatrice Mingo, for giving us a very comprehensive review on active galactic nuclei, something that is a favorite topic to many of us. And you are indeed a brilliant astronomer, and we know your published works could be combined together into a research volume called The Hitchhiker's Guide to Radio Galaxies, since you've given us so much in terms of our knowledge of radio galaxies. And congratulations on being awarded the Ernest Rutherford Fellowship earlier this year, which you're carrying out at the University of Hertfordshire. We look forward to the research that you'll produce in the next few years and in future. So now we have time to direct some questions to Beatrice and also discuss how we can improve our understanding of AGN studies through theoretical and observational investigations. If you'd like to speak, please raise your hand if you're in the room, and if you're on the virtual platform, raise your virtual hand. Do we have any questions, any comments in the room? Yes. Izzy Garland.
Thank you very much, Beatrice. Sorry, I know because you're not in the room. I'm Izzy Garland. I use they, them pronouns, and I'm from Masaryk University, almost. I suppose, given that this is the all-inclusive AGN plenary, I was wondering if you had any insight. Sorry, there's a bad echo and it's throwing me off.
I can hear you well. I can hear you.
I was wondering if you had any insight into how we can encourage astronomers to use multiple wavelengths. I speak to so many people who say, I'm an optical person, I'm an X-ray person. How do we encourage exploration more and less pigeonholing?
That's what I've tried to do with this talk. As you noticed, I've tried to show you what things look at different wavelengths and try to make you understand what other people might be seeing based on, their favorite telescope, what wavelengths they're working on, and what you might actually be missing. I think it's really important, and again, as we go into big data, to try and understand what you're missing from your data. I think we're all multi-wavelength astronomers now, even if we work more on a wavelength than a different one. And platforms like this, meetings like this, where we meet very different perspectives, both, people working from very different approaches in very different places, in very different career stages. This is all contributing to people getting a broader view of these sources. So exchanging ideas, making sure that we use the combined catalogs, that we present the data and we combine them in a useful way for people, that is also going to encourage them to use them. This is something that in particular the radio has been bad at in the past. We are now fixing in the present and in the future, combining the radio data with multi-wavelength data, so people can actually use the radio data in a useful way if they don't have the ability to reduce them or don't have any familiarity with it, and they can explore the properties of these sources also from that perspective. So producing good data, disseminating your resources carefully, documenting what you do, and always questioning what you're not seeing, what things might look like from another perspective, I think is the way to go forward. It's something that we all have to do in the future.
Thank you very much.
Okay, we have another question in the front.
Thank you, Beatrice. This was a very nice talk. I was looking forward to it. So we've got so many classes of Asians. Are we ever going to reach a point where we are able to classify the sources in fewer, less classes, where we've got maybe 2 or 3 or so? Are we ever going to reach that point where we don't have a dichotomy between these two, between all the classes that we have so far? Thank you.
I think, in a way we do have too many labels, and some of them supersede each other. Some of them are sub-descriptions of all the labels, or they are based on more limited information that we are using now. So all the labels that are not useful anymore, we should probably get rid of, and we should stop using. We still need to document them so we understand why other people classify the sources as such. I think documenting and making sure that this is still on record is useful. But I don't really see how we can just put things in 2 buckets. The universe is just too complex for this. We can do that, we can classify something as an AGN versus not an AGN. That's probably the only thing that you can classify very clearly into a binary. But even in that case, something is not an AGN now, but it may have been in the past, or something is an AGN now, but it may not have been in the past. The important thing here is not how many classifications we have, but how useful they are and how they link to each other and what insights on the physical processes that are underlying. So we don't want to go too detailed, because then, this is not really applicable generally. But at the same time, we don't just want to, I don't know, I can call all of these sources the Mingo galaxies. That's not going to be useful. I need to, try and relate what these things look like with respect to existing classifications, with respect to physical mechanisms that we can still understand. I think it's very important that we ask about the physics, and I'm showing my bias again here. I'm a physicist first. Try to understand what's going on, what's producing things that look like like this thing that you're trying to classify. So no, I don't think we're ever going to end up with 3 or 4 labels, maybe on a large scale, but then we still need to be specific to really understand what's going on. But that's not necessarily a bad thing, as long as we understand this properly and describe this properly.
Okay, we have time for 2 more questions. Yes, in the front. Please give your name and affiliation. Thank you.
Hi, Hae-Sung Kang from Busan National University. So I want to hear your comments about the physical differences between this morphological dichotomy from FR1 and FR2 radio galaxies.
So the FR1, FR2 classification is based on morphology, as I said. FR1 FR1s are things that are bright in the center and faint on the edges. FR2s are things that are bright on the edges and faint in the center. And there are different mechanisms going on here. So this brightness is tracing where the jet is disrupting, where it's depositing most of its energy. In an FR1, the jet disrupts early, so most of the, it disrupts close to the center, and it's depositing most of its energy around the center of the galaxy, while in FR2s, most of the energy is deposited at the edges. And there's a combination of parameters that give rise to this. So it's a combination of jet power and environment. If you have a jet with equal power, if you have a low density environment, that jet can just travel on undisturbed and will form an FR2, regardless of how low power this jet is. If you don't have anything to stop it until you reach a large distance, this is always going to form an FR2. If you have a very dense environment, up to a certain physical limit, you're going to disrupt the jet and you're going to form an FR1. I say up to a certain physical limit because we don't have infinitely large galaxies. So there is a limit to how large a galaxy can be. So for the same jet power, you can produce different morphologies based on what your jet is traveling through. And it's understanding how jet power and environment play with each other that is allowing you to understand what these classifications reflect in terms of the underlying physics. So yeah, the physics are important. This is a morphological classification based on what things look like, but it links to processes that are underlying. So it's important not to just put things in boxes, but try to understand what's going on. I hope this answers your question.
Okay, there are some questions, in fact, too. Stas Shabala?
Hi, Beatrice. Stas Shabala, University of Tasmania. Thanks for a great talk. I have a question on cross-matching, particularly of radio galaxies to multi-wavelength catalogues, because it's very hard to do any physics with radio galaxies if you don't know how far away they are. And in particular, I'm thinking of the duty cycle of AGN and the difficulty in cross-matching remnant radio galaxies with hosts. Can you comment on the most promising methods to do that?
That is indeed quite challenging. So effectively, the physics underlying this is, once you switch the jet off, the plasma that is in radio galaxy lobes and hotspots and jets starts relaxing and starts losing its shape. And you stop seeing it visibly at high frequencies very quickly. But because of the properties of synchrotron radiation, I can tell you about, the most energetic electrons radiate their energy away faster. If you go to low frequencies, you can see very old electron populations that are, hundreds of millions of years old, even maybe up to a giga-year old. So you can see some of these very relaxed structures that arose from jet emission. You can see them sometimes, blobby things in clusters or even isolated ones, but you can't actually pinpoint what galaxy they came from. If some of the structure is too amorphous and it doesn't really have some sort of symmetry that you can use, it doesn't have some characteristic that you can use to link it back to the host galaxy, it's really, really tricky to understand where it's coming from. And as Stas said, if you don't know where it's coming from, you don't know how far away that object is, you can't really infer the properties of a source if you don't know its redshift. If you don't know then you don't know its luminosity, you don't know anything else. So I think some of the most promising methods, if you have some symmetry, something like a ridgeline or something that pulls out some of that morphology, little enhancements in emission, and maybe using some some multi-frequency radio data to understand where the under emission is and where the near emission is a good way of pinpointing what your most likely host is. We also know, again, that the hosts of radio galaxies have certain characteristics. They tend to be more massive galaxies. They tend to live in clusters rather than groups. So pulling out multi-wavelength information, SED information on the different sources that you're seeing can also help you match this very blobby emission to the most likely culprit that's caused this emission in a cluster, which might not necessarily be in the center anymore. Galaxies travel through clusters, so they might have left that emission behind. I think with current data, we can get decent answers for many of these sources. They're not perfect. They're not going to be perfect. I think we're probably going to need some modeling to understand these better, to trace these better. And we can only do modeling once we have enough examples that we can use. So there's some good examples from LOFAR. For example, there's some LOFAR-led work that is interesting in this context, but we are going to see a lot more in future surveys with the SKA, and as we increase LOFAR to map the entire northern sky. So it's sort of half an answer to the question. I don't have a definitive answer to this, but I'm hoping that eventually we will get some good answers on these amorphous remnant structures.
Okay, thank you. Is there one more question that we can have?
Hello, Beatrice. Thank you for the lecture. I'm Luana from University of São Paulo. I work with Blazor, specifically variability, and using Fermi-led data, so I'm working with gamma rays. But I'm interested about this cross-match and different wavelengths. Do you think it's worth it regarding variability? Maybe there are properties that I can cross-match regarding, because it's variable from radio to gamma rays, but I don't know if the time scales will match or something. Do you have recommendations or comments on it, please? And thank you.
So that's actually quite a complicated question. Gamma rays have low spatial resolution, so matching the gamma ray emission to the other wavelengths is really, really challenging. I think the first thing you need to ask is what physical processes are driving the gamma ray emission. In your case, you're using Blazor, so you know that this is a jet that is pointing directly towards us, and that is going to tell you something about what the host looks like at other wavelengths. It might be jet dominated, it's almost certainly going to be jet dominated at other wavelengths as well. So that is going to give you a likelihood of hosts within your uncertainty range, where you can associate your gamma ray source to a radio source, to an optical source, maybe even to an X-ray source, obviously considering the ability to detect these across multiple wavelengths. And a lot of Fermi data are sources that we still don't know what they are. We still haven't been able to associate them. In terms of variability in gamma rays can be very fast. It reflects very quick changes at the base of the jet, very rapid changes in accretion, also some jet precession, little changes in orientation in the jet. And this is not often, sometimes it's not reflected at all the wavelengths, even tracing back to the X-rays, even tracing back to the radio. And though some of the physical mechanisms are the same, the scales that you're mapping, the physical scales that you're mapping, and the time scales that you're mapping as a consequence are slightly different. So sometimes the radio can lag or can precede the changes in gamma ray or the changes in X-rays. I think it's still your best bet if you're trying to study variability. Obviously, get as many wavelengths as possible. If you can get semi-simultaneous or quasi-simultaneous data across multiple instruments, this is challenging, but it's the best thing you can do to try and map how this variability happens across multiple wavelengths. And the lagging between different wavelengths can also give you an idea of the physical structures, how they're changing, how the accretion rate is changing, and how the orientation of things is changing. So yeah, all I can say is, get as much data as you can across as many wavelengths as you can. And if you can get it all at the same time, that's perfect. I know this is not always the case, but even if you have archival data, you can use patterns to try and trace the light curve of that, see if the patterns of variability are similar to the ones you're observing in gamma rays or not, and try to understand why that might be the case. You might need some models to actually do this properly.
Okay, thank you.
Thank you.
Okay, and with that, we've come to the end of our plenary. Thank you once again, Dr. Beatrice Mingo, for an excellent and very interactive and comprehensive review on active galactic nuclei. Let's applaud her again.
Thank you very much for hosting me and giving me the chance to talk to all of you, even though I'm remote.
Okay, thank you all for attending, and our e-poster session for this morning resumes.
Yeah. can do so much more, though. It's fine.
Tumela
akekho umuntu ongakwenza eyedwa kodwa sibumbene singakwazi.
Akwabo Wamkelekile. Welcome to Africa.
Start with something, don't cheat on this. Background for your brain, try this. Wait, you can see 1 year longer.
Leave Africa. Welcome from our nation to a land of work. It's Africa. Go Africa.
Truth stop somewhere.
Let us color together like a multi-wavelength.
You suggested it. I mean, this time, but if we see that
we could use for again. We can make things a better place. We can build a stronger man. Let's come together. Yeah, let's come together.
Anyway, just the first iteration. I don't know what happens with the weight. Could be that they are evolving somehow, even if you only feed source. But hey, do a couple of source on the
of twin saver tissues,
including the normal.
It was quite a moment, hey? You feel it like there in the heart, tingling, wondering why is it all over? We want to stay. Did you feel that? I felt that. I had to wipe my tears there for a moment. That was a good job. Can we have a round of applause for that? That's right. Very nice.
Yeah, I'm looking
So we're going to get all the formalities out of the way. There's quite a bit, but we're going to move through it quite quickly. My job is to get us there to the other side, and we're going to have some fun bits towards the end, some more entertainment. That's all on the way. But let me start on a very, very formal note this evening. Welcome to the closing ceremony of the International Astronomical Union General Assembly, number 32, first one in Africa. It is over. It's like a comet. It's like an asteroid. You saw it. It came.
Real Gaia data process is to estimate the weights.
And you must.
Each SI iteration.
And you know what? Did you have a good time in Cape Town, by the way?
I'm never diagnosed. Understand that you never So
I learned so much in the last couple of days. My heart is full. It really, really is. My soul is satisfied. But I'm glad it's over because the soles of my feet are sore. You know, I don't know if there are bigger convention centers than this one, but we had our offices over there. And then you had to go get something, right? And then you make your way back to the main hall and you realize, oh, I forgot something. And then you make your way back again. There was one day where I walked the distance like 3 or 4 times in 5 minutes because I kept forgetting something. So I hope that you got all your steps in. Got all your steps in because people are checking their watches, 5,000, 10,000 steps. But let me introduce you to some of the formalities very quickly. I'll invite 6 remarkable people onto the stage to come and join me. I will observe protocol with them a little bit later. So for now, you'll just know their names. I mean, you guys know all of them already. So can I have on to the 6 chairs in front of you on the stage, please, Deborah Elmer-Green. Please come join us. I don't know, I've got a thing for wanting to saying Italian names. Piero Benvenuti. It's really me selling myself to Rome in the next 3 years, where they go, that guy, he knows what he's doing. We should get him on the stage. Willie Benz. Will he or won't he is the question, really. Took you a while there, didn't it? It's okay, it's okay. You know, it's no longer a comeback laughter, it's like after 3 seconds, right? Can we be joined by Diana Worrell, please? Charles Takalani, come and join us on stage, please. And Angus Patterson, please come join us on stage. Oh, sorry. I had the wrong Takalani, my apologies. Like I said, it's the why I said I will observe protocol a little bit later, because if I get something wrong, then you can fix it for me. So there we go. The first repair of the evening. I'm tired, folks. Jeez, I just told you, my feet are sore. Forgive me, I speak with my feet. All right, so let's launch right in. There are some moments that we need to observe. We're handing over this evening to Rome, sadly. Cape Town. We lost to Rome once before. Do you guys remember? It was in Olympic Games a long, long time ago. And then it was us or Rome, and Rome got it, and we weren't happy. This time we're okay with it, I think. It's not the Olympic Games, even though it's on at the moment. So I want to hand over to the outgoing president to come and address us about some matters that she has on her mind, I'm pretty sure. She's been fabulous. Did you guys see her dancing the other night? I've got video if you want to come see me backstage of her doing a thing. Better than me, mind you. Deborah Elmer-Green, please come join us on stage.
Africa, you did it! Woo! Honored guests and participants, what a remarkable 2 weeks we've had, celebrating the, let's say it again, first ever General Assembly on the African continent. The engaging lectures, lively discussions, and interactions have forged new friendships and collaborations. Congratulations and special thanks yet again go to Kevin Govender, Charles Takalana, Vanessa McBride, and the amazing NOC for their organization, along with the help of the AFAS and all the volunteers. Yeah. My speech is going to be twice as long as planned because we got a lot of people to thank. Thanks too to the IAU Secretariat for their role in this, Rosaria D'Antonio and Lena Canis, assisted assisted by Rebecca Rossi and Patrick Chavala. I thank the sponsorship of DSI and NRF, along with support from the Simons Foundation, Kavli, Gruber, and Shaw Foundations, and many others. I'm so grateful to all of the participants, both in person and remote, for contributing to the success of this historic General Assembly, which certainly surpassed our high expectations. To all of you. Yesterday at the business meeting, we passed the statutes revisions and 3 resolutions, and we elected new leaders. The newly elected executive committee members are President-elect Brian Schmidt, Assistant General Secretary Laura Ferraris, and Vice Presidents James Shabuzi, Monica Rubio, and Grazina Tratfasin. I think you should all just stand up for just a moment so everyone can see your faces. For the committees, we had votes yesterday, and the results are in. The election of the Finance Committee, the 4 new elected people are Daniela Lazaro from Brazil as chair, Isabel, we'll do each committee all at once, that'd be quick. Isabelle Grenier from France, Aruna Goswami from India, and Isabel Marquez from Spain. Now we can. For the membership committee, the 2 new people are Elaine Dorosandaram from France and Ivana Melik-Zitnik from Serbia. For the resolutions committee, there's no fixed number. The executive committee coming in will determine the final composition, but the top vote getters are Paula Benaglia from Argentina, Annie Robin from France, and Alice Monet from the US. For the special nominating committee, 4 new members, Paolo Caselli from Germany, Marika Brancisi from Italy, Renee Alejandro Mendez Boussard from Chile, and Connie Ertz from Belgium. Congratulations to all, and many thanks for your willingness to serve. One of the duties and privileges of the Executive Committee is to select the location of future General Assemblies. I thank all of the bidders for their outstanding presentations and proposals to host GA 2030. It was an extremely difficult decision, and I know that some of you are going to be disappointed today. It's inevitable when we have a wonderful set of proposals and we have to just select one. But I thank you all for the hard work that went into your preparations. I now have the pleasure to announce the location of the 34th General Assembly. It will be in Santiago, Chile. It'd be the first time in Chile and just the 3rd General Assembly ever in South America. As I leave office, I wanted to reflect briefly on my past few years in office, starting as Vice President in 2015, and to thank so many people with whom I've had the pleasure of working. First was the first PhD division prizes that were awarded in 2016 following the suggestion of the then division presidents. The IAU strategic plan for 2020-2030 that I helped write as vice president along with past president, then president Aveen van Dijk, and then president-elect Aveen van Dijk, way back when, and other executive committee and other office members was approved at the 30th General Assembly in Vienna in 2018 when the new category of junior members was introduced. When I was president-elect, the IAU continued to realize more of our strategic plan goals with the establishment of the Office of Astronomy for Education in 2019. Also in 2019, the IAU held a worldwide celebration of IAU 100, led by Aveen, in honor of the IAU centenary. We established the Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference in 2022 as a countermeasure to a previously unforeseen threat to astronomy. We launched the Outreach Development and Education Prizes at the General Assembly in Busan in 2022 that Aveen initiated, and the Executive Committee Pro-Am Working Group was formed. These all further the goals outlined in the strategic plan. I took office as president in 2021 at an interesting and challenging time. The world was in the midst of the COVID pandemic, so our transition of officers took place at an online General Assembly business meeting. Although we had many online meetings, Willie and Diana and I didn't meet in person until the executive committee meeting in Paris in April 2022. Nevertheless, we forged strong bonds and enjoyed working as a team. So rather than the usual 3 years before a General Assembly, I presided over one at the end of the first year in office, of course, at the General Assembly in Busan in 2022. And now, just 2 years later, I've had the privilege of presiding over a second one. I'm extremely grateful to our hardworking staff and directors in our offices, including Kevin Govander, Marcus Pussell, Kelly Blumenthal, originally Lena Canis, Itziar Eritzaga, David Mota, Piero Benvenuti, Connie Walker, Federico Di Bruno, Richard Green, as well as all of the IAU members whose volunteer efforts have led to so many successful initiatives around the world as we all saw our way out of the pandemic. The world has truly changed since then, and I expect we'll continue to evolve in our practices. I have so many more people to thank, so bear with me. I want to thank them for their help within the IAU over the past few years. It's been such a pleasure to work with our secretariat. First, Rosaria D'Antonio, our head of administration, who is the heart of our organization. I thank Madeline Smith-Spanier for our earlier years together, and I'm pleased now to have Lena Canis as our membership coordinator. Much of the work of the IAU is carried out by our divisions, so I also thank our outgoing division presidents, Danielle Hestrofer, Gabrielle Giovannini, Richard de Grijs, Isabel Grenier, Christina Mandrini, Antonella Barucci, Andre Pescia, Monica Rubio, and Kim V. Tran, assisted with help from Christina Papascu. I'm so grateful to an amazing executive committee, including outgoing Vice Presidents Laura Ferrer-Rees, Daniela Lazaro, Junichi Watanabe, as well as our continuing Vice Presidents Susan Kang, Ilya Yusaskin, and Solomon Tessima. I'm grateful to our past officers and advisors, Teresa Lago, and especially Aveen Van Dishek for her helpful advice, guidance, insights, and friendship. I've greatly enjoyed working with the officers. I thank Ian Robson, who started as Assistant General Secretary with me way back, and then Jose Miguel Rodriguez Espinosa when he took over after Ian and became General Secretary, and especially Piero Benvenuti for coming back as Interim General Secretary in the last few months. I'm very grateful to Willie Benz and Diana Worrell for our teamwork and camaraderie through both difficult and good times. Okay, I'm not going to do this. I know they will be excellent leaders for the next triennium and wish them and Laura Ferrer-Rees and Brian Schmidt and our new VPs, James and Monica and Grazina, all the best as they lead the IAU forward. Lastly, this is the hardest one. I thank my ever-supportive husband and favorite collaborator, Bruce. Thank you all for the incredible opportunity to serve you for the past several years. It has certainly been one of the highlights of my life. The flag handover to Rome will happen at the close of this ceremony to launch the countdown to the 33rd General Assembly, and I look forward to seeing you all in Rome in 2027. Meanwhile, with your help, we'll continue working on the goals of our strategic plan, bringing astronomy to all. As we return home, we'll carry fond memories of beautiful Cape Town and our indelible connections, which are the essence of our General Assemblies. Let's all continue to work together as we share one sky, using astronomy for a better world. Thank you. Thanks so much, but before I turn the mic over to Piero, just another note. Piero, we're very grateful for your unselfish willingness to return to service as Interim General Secretary through the past several months. By way of thanking you, the officers and Secretariat have been working with Gareth Williams and the Working Group on Small Body Nomenclature. I'm happy to report the following 2 pronouncements. First, there's a new asteroid naming. Asteroid Piero Benvenuti, named in honor of Italian astronomer Now, this is the nasty part. Named in honor of Italian astronomer Piero Benvenuti, born 1946. It has to be in there. In appreciation of his long service to astronomy as the IAU General Secretary, 2015 to 2018, and as Interim General Secretary, 2023 to 2024, he is Professor Emeritus of the University of Padua. Piero spearheaded the defense of dark and quiet skies for astronomers and as a cultural heritage of humanity. But wait, there's more. Another asteroid naming. To thank both Piero and his understanding wife, Beatrice. Asteroid Umberto Benvenuti is named in honor of Umberto Benvenuti, 1989 to 2005, son of Beatrice and Piero Benvenuti. Umberto loved to explore the galaxy with his brother and best friend Eugenio in their imaginary spacecraft. He gave his family the power to face any difficulty and help them appreciate that we are all part of the same universe. I also want to note that these 2 asteroids were discovered together in the sky. Thank you, Piero.
Well, you know, I had already difficulties in preparing my second outgoing speech. But after this extraordinary announcement, everything I prepared becomes utterly inadequate. And so I have to scratch my talk and reset my thought quickly. What can I say? I mean, I'm dumbfounded from the token of recognition that goes well beyond any regular word of thanks. So I thank all the officers, you, Deborah, Diana, and Willie for this very thoughtful dedication. And if you give me a moment to recover, I may use some of the speech that I have prepared, because what I wanted to say is that the main reason I accepted to come back as a General Secretary at interim was the nice memory that I had in my previous regular term, working very hard with the officer of the time, Silvia Norio, and that intense work to defend and foster astronomy created a very strong and deep friendship that was the best reward of the time I spent with the Union. And what you just did is a clear proof that I was right. Because, you know, if you had labeled an asteroid with the name of the outgoing General Secretary, that would have been terrific. In fact, it is terrific. But that was, in a sense, unstandable in the realm of a normal relationship among colleagues. But what it did, mentioning our late son Umberto, signified the profound friendship that has been created among us. And there is more than that, and we already mentioned. Because honoring our late Umberto, you're also honoring his mother, my wife Beatrice, who not only dedicated her life to Umberto, but also sustained me all along, and with her wise, constructive criticism, in particular during the period I spent with IAU, and especially during the last few months, very intense few months. So I'm doubly indebted to you. And now, adding any other words to me, my outgoing speech will be out of place. So I think I would conclude using the word that I tend to say in my speech. Arrivederci a Roma, however, as a normal guest that time. Wait, I think I owe you an additional remark. I'm not sure I'll be able to do so, but maybe Beatrice can help me once more. What I want to say is that our son Umberto was a real great gift to us, and not only because of his extra chromosome, but because it taught us a big lesson. And the lesson was that the unconditional relationship that you can create among people doesn't need any support, any physical support. You don't need to be able to speak, you don't need to do special gestures. Maybe an innocent smile is helping, but it's not absolutely necessary. And once you realize that this relationship, which is as real as the sun, the moon, and the stars, live outside the boundary of space and time and cannot just be buried under a gravestone, then all of a sudden you have a glimpse of what our ancestors would call eternity. And from there on, you don't fear anything anymore. And your life is replenished by a great feeling of hope and peace. That is what Umberto did to us. And now that he's smiling to all of us from higher up in the sky, I wish he can do the same on behalf of all the kids like him, very special kids, and convey to you the same sentiment of peace and hope. And that will make this moment so extraordinary, not only for us, but also for you all, my friends. Thank you very much.
Wow. Is there a better accolade than having an asteroid named after you? A Piero Benvenuti blazing through the skies. That's amazing. I love that. I just hope it's not one of those asteroids that ends up threatening the Earth at some point or the other. Because then you might want to take your name off it at some point. Because Piero Benvenuti hitting the Earth and causing the extinction of mankind is not a great legacy. at all. I'm sure it won't. He's a safe point, all right. Speaking of incoming, the incoming president of the IAU is Willie Benz. Sir, please come join us.
Distinguished guests, ladies and gentlemen, dear colleagues and friends. Finding the right words to express what we just lived, to express what we have experienced over the past 2 weeks here in Cape Town, to acknowledge the legacy of this event for astronomy on this continent and beyond. And obviously to thank all those involved in this organization. It is more than a challenge to find these right words. It's almost impossible. However, our President and Secretary General have already been very eloquent in their expressions of gratitude, and I can only echo their words. Kevin and his team have worked wonders. As I reflect on the past 2 weeks, I think it is appropriate to recall the vision of the organizer at this closing ceremony. And I quote, "This is not simply an opportunity for astronomy. This is an opportunity to change the way the world sees Africa. When a continent so often looked down upon can lead the world in a field as technical as astronomy, then we change perceptions, we challenge preconceptions, we shake unconscious biases, we make the world think differently about the potential of all people in the world to contribute to the human endeavor." Wow. Have we achieved that? Have we succeeded in making the world think differently? I would argue that in a way we have. It has taken us 100 years, but we have finally caught up, and you made it happen. Astronomy on the African continent is certainly a full and respected member of the family. However, as in all families, relationships need to be nurtured over time. So when we return home, let us remember more than the beautiful scenery of Cape Town, the warm hospitality of our host, and the excellent organization. Let us remember that together we are pushing the frontier of astronomical knowledge in a collective effort to better understand the universe we live in, our origins, and our future, and to make the world a better place for all. Let us remember that in this endeavor, we need everyone, and everyone matters. Together, the IAU family is committed to excellence in everything it does for science and society. Nothing less is needed to meet the scientific and societal challenge that lies ahead. We look forward to working with all of you over the next 3 years. Finally, GAs are the rhythm of life in the IAU. And at the end of a GA, a number of people leave office whose work has enabled us to make progress towards achieving our goal. I get always trouble with papers. I would like to acknowledge their effort and dedication and express my deepest gratitude to all of them. Deborah mentioned a number of them. But a special mention goes to our president, Deborah Elmergreen, and our interim General Secretary, Piero Benvenuti. Together, Together they have steered the IAU with professionalism, efficiency, and above all, passion. Thank you to all.
Big shoes to fill and capable from the sounds of it. Congratulations. We'll do the official handover shortly, but he'll be supported by a General Secretary, of course, taking over from Piero Benvenuti. Please, a round of applause for Diana Worrell.
So, dear distinguished guests and colleagues, so the last 2 weeks have been truly inspirational as we've met to discuss and explore the science that stimulates us and motivates us to share that exploration with others. The General Assembly has allowed in abundance the opportunity for exchange of ideas, both through arranged sessions and more informal encounters, whether in person or online. The scope's been such as to extend our exposure to new developments in areas with which we're less familiar through prize talks and invited discourses. I'm grateful first and foremost to all participants for making this a truly engaging General Assembly. I extend my particular thanks to the hosts in Cape Town and all who've contributed towards sponsoring and organizing this General Assembly. For those associated with just one facet of the IAU, perhaps mostly through division, commission, working group, the GA has provided the opportunity to learn more about the broader portfolio of IAU activities, including the work of our 4 offices and the Center for the Protection of Dark and Quiet Skies. These are partnered with institutions in various cities across the globe and involve large networks, large numbers of individuals from the community through the pivotal role in advancing and protecting astronomy worldwide. And that's what the IAU has a recognized pivotal role in advancing and protecting astronomy worldwide. And so we should feel proud to be part of that. Now, while ambitious endeavors require funding, I'm particularly grateful to the many who are giving freely of their time, initiating and supporting a range of activities with our shared goals. So as we close this General Assembly, I move humbly into my role as General Secretary for the next triennium. I trust in your support as we work together with common purpose, albeit recognizing that we might sometimes stumble over mechanics and challenges along the way. I wish safe travels to those of you returning home and look forward to meeting you in 3 years in Rome, if not before. Thank you.
Sometimes the brevity of the speeches take me by surprise. I think there's more coming and then they're done. I love that. Move right along, shall we? Thank you, Diana. Can we invite the Chief Director of South Africa's Department of Science and Innovation? He's joined us a little bit earlier, particularly responsible for astronomy. I got the Takalanis a little bit mixed up earlier. So let me not this time. This is Takalani Nemangwane.
To the outgoing and incoming IAU Executive Committee, the President of the African Astronomical Society, Professor Thebe Medupe, Dr. Angus Patterson, the NRF Deputy CEO responsible for national facilities and infrastructure. On behalf of the people of South Africa, and this government, and in particular, our minister, I would like to convey our deepest gratitude to the IAU family for embracing us and descending on our shores and allowing us to host the 32nd IAU General Assembly. It felt like a festival of astronomy. We truly felt your presence, your love and your support. And we experienced the unique and diverse, rich networks and partnerships that you brought to the African soil. As someone who was involved from the beginning, when the idea of hosting this event was first conceived, I think it was Professor Patrick Wout who first approached me about the idea of South Africa hosting this General Assembly, and I immediately agreed to it and facilitated the involvement and the support of our government. I then led the South African delegation in Hawaii, where we first submitted our bid. Of course, we lost to South Korea at that time. So let me comfort those who did not win. We were in the same shoes in 2015, but we did not give up. We resubmitted, and again, I led the South African delegation to Vienna, and it was a very memorable and emotional day when we were awarded the right to host this event. I can remember dancing with joy and, wrapping myself with the South African flag. I then led again another delegation to South Korea, to Busan, when we were handed over the baton to then, begin to work to plan to host this event. I want to believe that this is not the last time this event is coming to Africa. And I want to believe that it will surely no longer take another 100 years. Because we've got a plan to make sure that it doesn't happen again. And that plan is working through the African Astronomical Society to continue to develop astronomy in Africa and to mobilize the African community and to take the legacy of this event to make sure that African astronomy is no longer the same again. I think it was in 2018, when we were at the European Astronomical Society, we had a special session of Africa-EU partnership. When the African community was complaining about not having a body, although it was established but not active because of lack of funding and support, I then offered the African community that we can bring AFAS to South Africa, and I will make sure that we have the budget for it, and I will be there to support it. And therefore, since 2019, when the African Astronomical Society was relaunched, last year we had the 4th scientific conference of AFAS in Marrakesh, in Morocco. It was the first time AFAS was hosted outside of South Africa. And we will continue to make sure that it rotates amongst African countries so that we can continue to build African astronomy, but also to build the capacity to host events like this. And that is the plan that I'm confident that one of the other African countries is going to very soon submit a bid to bring back the GA back to Africa. During these 2 weeks, we not only gained weight because of all the food that we've been enjoying, but we gained so much knowledge, wisdom, and understanding. We gained so many friendships and partnerships. And this event has left a legacy that will leave fond memories about these unique and rich experiences. I trust that you all enjoyed African hospitality, the energy and the vibrancy of our people, and the culture, the food, and everything. And we hope that many of you will come back very soon so that we can continue working together in building African astronomy, which I think can only be good for the global IAU endeavors. So, on that note, I would like to wish you a pleasant and a safe trip back home. And in Zulu words, I will say, hambani kahle, niphinde nibuye futhi. Thank you very much.
Takalani Nemangwani, thank you so much, Director of Astronomy at the DSI. You know, I love the fact that we've gained all the knowledge. It's the weight that I'm worried about. Because I speak for myself, and I'm sure you can probably agree, some of you anyway, that we need more weight like we need to be part of a new WhatsApp group, right? Because that's always fun. Added to another WhatsApp group. So I was added to another one for this whole, it was so much of fun. 295 unread messages, I can prove it. Shoo. All right, thank you, Takalani. The National Research Foundation had a lot to do with putting this event together, and it's only fair that they come and address us. The Deputy CEO is Angus Patterson.
Normally when you get asked to speak sixth, it either means best for last, or it means you're picking up the bill. I believe it's the latter. No, on behalf of the National Research Foundation, I think we'd just like to say a big thanks. When you start a conference, you always start off with this long list of protocols. It's far easier at the end of a really good conference just to say, thanks, friends. And that pretty much covers everything, because that's how you arrive. You arrive as colleagues, you arrive as working partners, sometimes you arrive as rivals. Hopefully at the end of the conference you leave as friends. I think a key thing that happened in South Africa was, you know that South Africa went through a very traumatic history. And in '94, when we came into the democracy, we had a chance to make a lot of things change. And I must say, we have a system where the national facilities are all under one office, which I'm currently heading. And that includes everything from subatomic physics to ships to distributed environmental infrastructure. So it's a whole range of things. So you can imagine in the mid-90s when South Africa was in a very difficult position. Finances were not great, but we had a chance to make a new vision. And a lot of people would have said, well, we've got things like water that are big issues, that the vast majority of the population didn't have running water. We had issues like electricity. There were a whole range of host of issues that we could have invested in. But that's not the way South Africa does things. South Africa says, no, actually we're going to show the world what we can do. And we're going to do the hardest thing. So, what's pretty hard? And we said, well, we've got a geographic advantage in terms of the Karoo, in terms of dark and quiet skies. So let's show the world something really hard. Let's really demonstrate to the world what South Africans and Africa as a whole can do. And we started off with a very small community. We had a history at SAO over 200 years. We started off with salt. I see Brian sitting up there, the chair, looking at me. So with our international partners, we built the biggest optical telescope in the Southern Hemisphere. Then, of course, we know of the Meerkat and the whole SKA, and then on to the SKO and SKA Mid. And those are all really things to be really proud of. But the big question, and what makes me very proud to be a South African right now, and to be very proud to be an African, is that you came. We took the chance, but really the proof in the pudding is when the world comes to us and comes to share their experiences with us and to understand what we do. So yes, it is time for Africa. And South Africa was very brave in the 90s to make such a big decision, to invest a lot of money in a very niche area. But I think that this General Assembly clearly shows the deep and very brave thinking that was done then in terms of understanding why you would want to invest in astronomy, in terms of the returns in astronomy, in terms of showing the world what we're capable of, in terms of, I think the earlier speaker was talking about the prejudices, the unsaid things, that those really are not valid. Africa is very much part of the world. We have a huge amount to contribute. We can take on the biggest challenges, and we do take on the biggest challenges. To finish off on a lighter note, I'm a marine biologist, but I had worked with Kevin on a number of different science festivals. So when I arrived in the Deputy CEO's position, he said, I need to have a chat with you. So I said, oh, okay, Kevin. He says, no, we're having a General Assembly. So I said, oh, that's very nice. He says, no, Angus, this is the IAU General Assembly. I said, oh, that's great, So he says, Angus, it's the biggest astronomy event in the world. And I said, oh, okay. So that went fine. Then he took me through it and everything, and I got super excited. I understood why Takalani was so invested in it. I did all the background reading and everything, and then Kevin brought me the budget, and I went, oh. Okay, well, that's a really good one. It's a really big budget. But the kicker was in clause 17, which said, no, Angus, you're liable for the budget. The NRF regards whatever was spent on this conference, particularly from the DSI, all the sponsors, and everyone that contributed so much, as being really well spent. I mean, I look at us, I look at what I see up here, I see us all going home, I see us speaking about Africa, I see us speaking about South Africans, I see us speaking about technology, and I see this as a real impetus and legacy of the conference. So Kevin, thanks for arriving in my office and saying that, you got this little matter to chat about. I'm not going to say much more on the thank yous, other than there are obviously some very deep thank yous to the South African team, but I think I'm not going to take that away from Kevin, and in the young people's parlance, throw shade on him. So over to you, and thank you very much. South Africa would just like to say, it is Africa's time. We are here, we're staying here, and we really want to participate and work with you. Thank you.
Can I have a round of applause for our speakers, everybody? Thank you very, very much. While they're going to leave us in just a moment, I'm going to invite our next speaker onto the stage while we make some changes up here. I know we are stretching this out for as long as possible, holding on to that flag for as long as we can. We don't really want to give it to Rome, but we must. But we get there. We're just kind of stretching it as best as we can. So I introduced him to you last time, and I'm going to hand the mic to him in a moment, but really is an admirable young man for having directed everything that's happened over the last 2 weeks, over the last few months, in fact, that got us to the 2 weeks, and continues to be very much hands-on, involved practically, on a daily basis, carrying things around. He, of course, needs very little introduction, but allow me a little bit of levity, will you? It is the chairman of the Knock Knock. Knock Knock. Kev. Kev Ingenious. Mr. Governor.
We've made it. So just to build very quickly on what Angus was saying, this really is the culmination of decades of investment. This started in the 90s with those visionary South Africans saying, let's invest in this hard science, and this is the culmination of that. All the work, all our facilities, all the researchers, we've now arrived. And like Angus says, we're ready for the world. Let's work together with Africa. I said in the opening, let us all be children of this GA. Let's go forth and let's keep building those relationships with the African continent. So thank you for being here. So many people have asked me this, so I thought we should get some statistics. In-person participants, we just over 2,050 in-person participants. 600, well, that's all of you. You can clap for yourself later. So just over 2,000 in-person participants, just over 600 virtual participants from altogether from 107 countries. We had 647 students. And from the African continent, we had 841 participants. I think this is the highest representation of Africa in any astronomy meeting. So thank you for letting us have this opportunity. One more, we know this was open access, so the YouTube views, excluding the last 2 days, which are still being counted, I guess, is 15,000 views on YouTube with 4,800 unique viewers. So I think it was worth the investment. Okay, very quickly to run through, we have to say thank you to all the organizations that supported us. I hope I don't miss any, but if I do, forgive me. Tomorrow sleep is scheduled, so I'll be sharper after that. So of course, our Department of Science and Innovation, National Research Foundation, and African Astronomical Society, the three big logos there. Thank you very much. Let's give them a separate round of applause. Then running through Simons Foundation, SKAO, Brand SA, NAOJ, these are our big sponsors, AIP, ESA, AWS, our prize sponsors, Kavli Shaw, Gruber, the LSSTDA, the various embassies, Spanish, Australian, British, Finnish, the Department of Tourism, the WESCRO and the Western Cape Convention Bureau, the National Academy of Sciences in the US, the National Academy of Science and Letters in Norway, SPIE, Heising-Simons, AAS, and all our exhibitors, everyone that participated, contributed to making this a huge success. So thank you to everyone. And a very special thank you, a specific thank you. The partnership with the LSSTDA was part of a crowdfunding initiative to raise funds for more African participation. And there were donors from from individuals all around the world. We had a donate your registration program where people from around the world contributed towards allowing access to this conference to more, especially African participants. So I want to give a special thank you and recognition to our partners at LSSTDA and all the individual contributors. Thank you. And another special mention, making this conference accessible was about making sure that the Zooms were working, making sure that the YouTube stream was working, making it possible for participants to join virtually. Our partners with, in TFOM, the future of meetings, I want to send a special thank you to them because they worked super hard. That whole spatial environment that was built for this conference, the work that Vanessa Moss and the team did has been incredible and has helped us to understand, to learn, and to make virtual possible. So thank you very much, the future of meetings. In addition to that, you know, one thing that we had here, we had a special relationship with all our suppliers. So I want to say a special thank you to IVTM who did the technical, to Hot3D that did our exhibition and our branding, to Blend who did our decor, and to the CTICC, this convention center. They've been really part of the team and not like service providers. So let's give them a hand. So I know everyone is very happy and stuff. It's end and clapping, but things did go wrong. Things, you know, every time I was made aware of something, I know that every now and then there were bugs. Every now and then, you know, someone online couldn't hear or something like that. Thanks for your patience, and I think thanks to the technical team and others who jumped in and helped. So you know, when you push the limits of something, you're going to have a few things go wrong, and I want to acknowledge that. But we pushed hard, and we innovated. And we want to challenge every one of you in everything that you do. Push hard. When we said open access, people said, nah, that's impossible. When we said free childcare, how are we going to afford that? When we said fully hybrid posters, 100 screens with 100 Zooms, everyone said, yeah, that's impossible. And you know, when we push things like that, there are things that's going to go wrong. But we learned so much, and we really, you know, if you have a vision of accessibility, then we must push ourselves. This massive outreach program, this massive grants program, we pushed ourselves hard. And why did we do it? Because you are in South Africa. We are children of Nelson Mandela, and he said that it always seems impossible until it is done. So let's talk about the elephant in the room here. Everyone here thinks I'm awesome, right? But every time that you say thank you to me as we leave, I want you to think of everyone that comes behind to make this thing happen. everyone that works behind the scenes that doesn't get to stand on stage here. And so in the opening, I said that we are all human first. And I am defined by my family, my wife Carolina, and the kids. Every one of us is defined by that. And our team has been amazing to do this. So I want to call on all our team now. I want all our National Organizing Committee, all our volunteers, please guys, come onto stage, join me here. Yeah, now you can. Whether it was the people in the registration desk, the people in the technical support, you've got our volunteers, the people that went out to the outreach teams, the people that helped with the grants. Please come forward. Come and have your moment here because you deserve this. Let's welcome them to the stage. Keep on coming, keep on coming. You can see how many people were involved in this. This is not something that we can do as an individual. It's not something we can do as a small team. This is how many hands it takes to make this happen. Our posters team, our childcare team, all the suppliers, our IVTM, our technical guys, our cameraman who's taking pictures of us now, Bradley. Our Radio Astro team. Who am I missing? Come on, guys. Our finance team, our comms team. Oh, cool. Let's thank them fully. This is who made it happen. Stay here, guys, stay here. You can stay standing if you want, because I want to take a moment here. I would ask you guys to look into our eyes. Look into the eyes of every one of these people, because every one of them worked hard. It wasn't just them. It was everything behind them. We are all human beings first. And when you look at someone, don't just look at the science that they do. Don't just look at the work that they do. It all comes with a family behind them, a history behind them. We are all human before we are astronomers, before we are scientists. And we carry within us a whole universe of thought. We carry the ability to understand the universe as individuals. And when you look into someone's eyes, look past skin color, look past economic status, look past nationality, and see each other as human beings, because that's what we are first. So thank you, thank you, thank you, everyone. Thanks, guys.
Kevin, first of all, Mom.
Yeah, but also spend half of my time here.
So you go to your WhatsApp and then launch.
One more round of applause. It's taking so long. Come on.
Is it safe to come out? I was worried the stage was going to collapse there for a moment. I was also worried when Kevin said, look into their eyes. I thought, they're going to see how tired we are. Don't look into that. We're barely keeping our eyes open. But we'll get through this evening. We're waiting for the dancers to get into position. Then we're going to get the flags onto the stage. I just want you to note something. Kevin said something a little bit earlier. 173 countries represented here over the last 2 weeks. There's only 196 countries in the world, I think, or 95. 107. And there's only 195 countries in the world. So that's almost half the world was here. And I think that's fabulous. And I think there should be some sort of a record thing. You know, like how many countries can you get to your GA? The record is now at 107. Over to you, Rome. All right, let's get the flag and the dancers onto the stage. Can I get onto the stage the officials that will be in charge of handing over the flag to Rome, please? The South African delegation, Deborah Almagine, the outgoing president of the IAU, Takalani Nemangwani, the chief director of astronomy at the DSI, Angus Patterson, the deputy CEO of the NRF, Tebe Madume from AFAS, the president of AFAS. Come join us, please. Vanessa McBride, Charles Takalani, and Kevin Govender, the chairs of the General Assembly, South Africa, Africa, and Cape Town. So we need to immortalize these moments with the flag that we now have to send to Rome. Why are we sending it? Why can't we just keep it for the next 3 years? Do they need it now already? They don't need it. What are you going to do with the flag now? If we can do this official photograph, I will move myself out of the way for it. Balance, please, balance. Thank you. Can we have the Italian delegation to come join us on stage, please? Willie Benz is, of course, the incoming IAU president. The ambassador, please, Alberto Vecchi, is the scientific attaché for Italy. Luca Tiano, the president of INAF, Roberto Ragazzoni. The chairman of the LOC, Angelo Antonelli, the president of the IAU National Commission for Astronomy, Grazia Umana, and the national representative of Italy for the IAU Board of Directors of INAF, Ginevra Triccieri. So we would like to have a group photograph of the two delegations together at the flag, please. Because this is where you probably might not see each other again in this form as delegations. And South Africans, Cape Townians, Africans, this is the sad moment for us and the happy moment for the Italians and those from Rome. This is the official handover. Deborah and Kevin, if you could do the handover to Willie Benz and Mr. Antonelli, please. Oh, are they there already? Oh, there you are. All right. Sorry, I didn't see you. I thought we were still hanging onto the flag. Forgive me. Can we have a group photo of that? Thank you very much. And now we have to have the South African, African, and Cape Townian delegation depart the stage. A bit of balance on the stage. Thank you very much. Folks, you are looking at the IAU GA 2027 Rome. Ambassador Vecchi, the stage is yours.
President Emil Green, incoming President Professor Benz, outgoing Secretary General Benvenuti, incoming new Secretary General, South African authorities, ladies and gentlemen, it's very difficult for a diplomat to stand in front of an audience of scientists with a mic in his hands. I mean, they worldly recognized smartest people in the world. So I will confine myself to two things, just to avoid unpleasant comparison between science and diplomacy. The first, yesterday we had talks at my residence with scientists. I was feeling dwarfed by, in many occasions. So I will say just two things very quickly. And the first thing is to express the gratitude on behalf of my country to IAU and to South Africa for the organization of this historical General Assembly in this wonderful city of Cape Town. Thank you very much. Secondly, my gratitude to INAF for taking on the privilege of organizing the next General Assembly 2027 in Rome, to which you are all invited. Third thing, it's not two, third thing is felicitaciones to Chile, of course. Well done. So it's my honor now to introduce to you the real speaker, the President Ragazzoni of the Italian National Institute of Astrophysics. Presidente Ragazzoni.
Thank you, His Excellency, Ambassador here. Thank you to all colleagues and friends. I mean, it's an honor to be here, and it's an honor for us to host the next IAU General Assembly. I want to say, when I start to say, I want to say three things. Usually I remember one of the, I forgot one of the three by the end of the speech, but let's try. The first one is that we will love to have you in Rome, and we will love to be in Chile, and we will love to be again in Africa, maybe in one of the next. So I join what has been suggested by one of my speakers before for other African countries. So we had so much fun in this date, so we want again to be back in Africa in one of the next General Assembly. First thing. Second thing is that why we do this? We do this because we want to invent a new kind of ways to observe the sky. We want to make new devices. We want to understand better how stars or galaxy moves, what is there in a planet. Some of the questions looks like, is there chlorophyll in an exoplanet billion of light years away? What's the question? This question will carry with them a lot of technological development, a lot of new ideas, and the outcome will be transformational and so on. But, I mean, I have been honestly moved by a couple of asteroids that I understand are in a safe orbit, so there will be no risk, but they have a great representation, and for me I was really moved, and I think that they represent in a special manner that we do this not only for this, but as ultimate goal to make the whole world better and to have, better comprehension and make all the society better for this better comprehension of the universe and better understanding of each other on this planet, and to take care of everyone, even not the fortunate, that can easily look at the stars like we normally do, and we take this for granted. This was the second thing, so thanks Piero for reminding us all of this. And the very third thing, this is a bit, we had spent 2 weeks. I personally spent only the last fraction of it, sorry about that. And we had new friends, we had new ideas. Every time we exchange an idea, we all get richer, because I have also the idea of the other and vice versa. We have got a new idea, we have new proposal, and maybe we will think to this, and there will be more collaboration with countries that I would have never thought we could have a collaboration in the future. We have someone complaining that we could have more weight, and maybe we can have more alcohol, and because of this, I want to remind you that in the following minutes we will display video in which we will see myself and Angelo Antonelli. Angelo Antonelli will be the chair of the conference of the General Assembly in Rome. So I am the president, and he will be the chair. So if everything will be fine, I will get all the merit. If something fail, will be failure of Angelo. That's a hard job of the president, but someone have to do this dirty job. And So I think that we always thought within us we want to make another historic and memorable general estimate. We will do our best to do that, astronomers, and we also like to have great challenges. I would say it would be very hard to make more impressive, more historic of this special, but we will do our best. So if maybe it's possible, we can run the video right now.
We study the stars to know about the universe. And thanks to the state-of-the-art technologies produced by Italian companies, we can look at our own and other galaxies with adaptive optics that give us very high-definition images. We explore cosmic distances up to 13 billion light-years from Earth to understand the evolution of the universe. We analyze the atmospheres of the planets, of stars far from us, to look for extraterrestrial life. Italian technological excellence allows us to visit our solar system, to land on distant bodies and prepare for human exploration. We observe black holes, immense particle accelerators in the universe, cosmic rays, X and gamma rays, thanks to satellites and special ground-based telescopes capable of exploring the properties of matter in extreme conditions. With Italian satellites, we study the universe, but also terrestrial phenomena, such as gamma rays during lightning storms. Using cosmic rays, we also image the inside of volcanoes. With our instruments, we monitor the sun, as well as asteroids and space debris to protect our civilization. We are a dot, a small point to start from. Italian scientific and technological excellence finds answers that are useful for the entire planet.
Ciao to everyone. I am Roberto Ragazzoni, the president of the INAF, the National Institute for Astrophysics, the institution that takes care of the development of astronomical and astrophysics in Italy. And I am very grateful to the people, to the friends of the Republic of South Africa for this handover, and I welcome all of you in the next IAU General Assembly that will take place in Italy, in Rome, in 2027.
Estimated colleagues, I would like to thank South African organizer for this amazing General Assembly. And now is the time to invite all of you in Rome in 2027 for the next General Assembly. Rome is a very special relationship with the IAU because we hosted the very first General Assembly in 1922. But Rome has also a very special relationship with astronomy since the Roman period, through the medieval age, the Renaissance, up to the modern period, and we expect all of you here in Rome. Looking forward to see you here.
Recent years have seen new exploration of the universe through gravitational waves. LIGO, Virgo and Kagra are revealing us the physics of stellar mass black hole and neutron star, also in association with gamma ray burst and kilonova. The pulsar-timing array are revealing signals at lower frequency. We are looking forward to meeting you in Rome in 2027 at the General Assembly to discuss the exciting new results of gravitational wave astronomy, and also to discuss the future of this field, and in particular Einstein Telescope, Cosmic Explorer and LISA, that are instruments that will enable us to reach the early universe with gravitational waves, and also to observe unexplored sources.
I just add, see you in Rome, and especially all our African friends. Thanks a lot again.
If we can have the final photograph of this group, please, with the VIPs on the stage. They feel very good about themselves now. Thank you. Thank you very much, ladies and gents. Being called strong men, the flag will be...
As you can see, we are learning right now.
You're absolutely learning. Don't worry about it. The flag's going to get stored away, and you might want to keep an eye on it, because we might just nick it and keep it here in Cape Town. We like that flag. Folks, give yourselves a round of applause. That was lovely. We have come to the end of the evening, the end of the closing ceremony. We will have one more performance from IAU Cultural Ensemble. Can I have a round of applause for them, please? And they really have something quite special planned for you guys. So stick around. I think you're going to enjoy it before I say goodbye to you. You know, you guys, you haven't even said anything about how beautifully I cleaned up for you this evening. Right? I went and shaved and a haircut and everything, and you haven't said a thing. Hey? I think I went through a bit of an effort, right? Because Radio Astro has kept me so busy I didn't get to clean up at all, which is really what I want to say to you. When you leave here this evening, you need to do me a personal favor, please. If you're on social media, any one of the social medias, on YouTube, please go and search for radioastro.space. And then like us and, you know, follow us and share our content. It's yours, by the way. You know, this is where we're going to be distributing all your wonderful content from all over the world. So make us famous. Why don't you? Do that this evening, and then I want to leave you with just a final thought that just struck me back there before I hand over to the IAU Cultural Ensemble. As Mr. Ragachoni was speaking, he's the president of Enough. And I was thinking, when is enough enough? And then it struck me. You guys are super smart, and you're starting organizations all the time. So I want to leave you with a cautionary tale that just struck me backstage. If you're going to start an organization, please consider the English acronyms and abbreviations for your organizations. And I'll tell you why, because I looked at AFAS, the African Astronomical Society, and I realized that they had to put the little F in there for a reason, right? And then it struck me that there's a new organization called the African Space Agency. That acronym doesn't quite work, so they put an F in as well. It's going to take you a moment. African Space Agency. There are kids in the house, I can't say it out loud. You think about that for a moment. Rome, congratulations. Thank you very much for the handover this evening. A big round of applause for Cape Town, Africa, South Africa. I'll see you guys online. A big round of applause for the IAU Cultural Ensemble. Ladies and gents, here they are.
ke tla go raga dinko tše he bana ba kgoši gape re fihlile banna gona bjale ke naka gore re boele morago ke gore re ba bontšitše gore na re bomang gore na re tswa kae gape nna re matlametsi gore badimo ba metsi mo re feta gona dimpša le dikatse ke ra bagalabe le basadi bana le bakgekolo ba re šutselela ditsela banna ba regena oria ga mphe moropo moo
They can just put it on. Up. Let's just the Up Ovuya Cultural Ensemble. Ladies and gentlemen, be safe, enjoy your evening from Cape Town to the universe. Over here. There we go.
Thank you very much and congratulations. Thank you very much. Grateful for your service as president. Great compliment from you.
Ah, yes, maybe he's on the side. Let's go see.
Thank you so much.
suerte hablarle ayer. Empezamos de ahí. Presidente. Thank you so much. See you. When will we see you? Will you come and visit Planet S again?
Yes, one more time.
Great. Before we meet in Rome.
Yeah.